Hello. We're supposed to try our stuff, right?
Yeah.
But doesn't seem to be anyone here.
You're trying your stuff. I tried mine and it worked with this one really easily.
HDMI?
HDMI worked like great. If you have a Mac, it should work even better. And I think there's, you probably know more than I.
I don't know. I'm just sort of, I
Like
plugged in before.
I plugged mine into so
I'll quickly try this and then you.
Yep.
Oh, this is not the right items.
You would rather. Oh, you already did.
Yeah, this is another one, but yeah, I think it's fine. Okay. So,
Did it work?
yeah.
Oh, okay.
So this is for you, I think.
Okay.
Let's go to here. Okay, I'm gonna grab some coffee.
Yeah, okay.
You can't control it through that, but go to the slides with
Yep.
sound on them.
Okay. I can't, I can't find my beeper. Why is that?
I have no idea.
Okay.
Oh, because it's on this screen. That's why.
Oh. I see. Okay. I didn't hear it. Let me see. I might have hit mute. Sorry, it's disorienting. One sec. Okay. Yeah. That's it.
Is that it? Just the one quick
Yeah. Is there a way to change that so that I can see the pointer
Here,
too?
let me see real quick. Yep, here it is.
Oh.
So it's like an extended screen. So if you go off the screen like that, you'll end up back on the
Oh, okay.
projector.
Thank you. Okay, good. Okay. Whew.
Tuition reimbursement. Now we can no longer offer that for that last year. So here's like a bill for $50,000. First in the tears. Yeah. Let her cry. Because they said you can come back to it for just come back for another year. And then you'll be fine. I can't do it. You can't. More importantly, you can't let her contact the university because then we need to get
Great organization here. Yeah, no, I'm very impressed. Yeah.
You're next after this, right? For the second?
Yes.
instead of it going all the way down, tuck it under. Basically,
Okay, we're going to get started. On time-ish. Throw a wrench into the system and start on time. So I have one announcement, and that is that we're going to try something that we haven't tried before at other conferences, which we're going to segregate the microphones in order to encourage more junior colleague participation in the question period. The idea is, we'll try it out here today, is that one of the microphones, say this one, will be for people who have tenure at some institution. and then over on this side, it will be for anyone who does not have tenure. And we'll alternate that way. And so that way maybe we can get, we're hoping to get, so I mean if you're a student or you're, whatever, a postdoc, and we'll try on the left, your right, sorry. We'll try that, okay? And so I'll leave that up to the session chairs to try to, because a lot of people aren't here, they won't know this, we'll have to tell them every time, okay? And we'll see how that goes. And we'll abandon it if, we're experimentalists. If it works, we'll use it. If it doesn't, we'll go to something else. Okay, it's my pleasure to introduce Adele Goldberg for the first talk of the day. Adele got her PhD from Berkeley in 1992, working with Chuck Fillmore. And had an enormously influential book in 1995 outlining the idea of construction grammar. The idea of construction grammar is that language consists of lots of small bits called constructions. For example, there's an infrequent construction, the more the merrier, the snowier it gets, the more people will come to our pizza party at 6:30 to 9 tonight. Or just a verb or a noun or a verb phrase. These are all constructions. Since then, Adele's built a huge influential research program studying constructions within and across many languages. She works on in lots of different ways studying this, including acquisition. I think she's going to talk about acquisition, processing, adult processing, and neural bases of language. She has many awards, including the lecturer at the 2007 Nijmegen lectures. She's a fellow of the LSA, inducted in 2014. She has a Humboldt Award from the German government in 2016, and there's a whole lot more. Adele.
Thank you so much, Ted. And really, thanks for a fabulous conference. I think we owe Ted a big round of applause. And thanks to all of you for making it out this morning. I know it wasn't easy. I'm also dripping wet here. So we know from a lot of work, especially over the last couple decades, that languages are impressively distinct from one another. So the question I'm going to try to address today is why and how do we learn the conventions of a language? And I think it's worth stepping back and asking what it is we need to do. And it's clear that we need to understand messages given forms for the sake of comprehension. And we also need to choose the forms in order to express the messages that we want to convey for the sake of production. So given those two simple facts, it seems clear that what we need to do is learn and use form-function pairings or constructions. So we actually like to talk about a lot of different situations. And luckily, we have different constructions that correspond to differences in function. So many phrasal constructions their function involves information structure, or their function is discourse related. So we have the topicalization construction where the fronted noun phrase is a new topic, like CUNY, I love it, and you're likely to introduce CUNY into the discourse and continue talking about it. And that can be compared, sorry, that was left dislocation. Topicalization, where you have a gap, like CUNY, I love, is often used for moribund topics. That is, things you've already talked about, but you're not likely to continue talking about. Other constructions convey attitude, so the NP him, the leader of the free world, the incredulity construction, or why read the newspaper, evokes disapproval or skepticism. And a construction that I've recently started working on with Thomas Erbst is exemplified by "It's good of you to have come," And it's clear that it requires that the speaker judges someone's action evaluatively. So you can't say it's tall of you to reach the top shelf. You can say it's big of you to reach the top shelf, but in that case, big doesn't mean big, it means something like generous. It has to be applied to an animate, so you wouldn't say it's helpful of the dishwasher to save water. And this is true in general for phrasal patterns. There's some sort of function. So the double object construction, if I asked you what moop means in she mooped him something, more than half of you will think of give. And others will come up with verbs that are closely related to give. And that's not an accident because the conditional probability of give, given that you have the double object construction, is about 0.5. Does anyone have any water? Sorry, it's okay. And if you look at all instances of the double object construction, oh, it's okay, it's okay. Okay, sorry. If you look at the double object construction in corpus data and then you have independent raters decide whether the sentence involves literal or metaphorical transfer. So one of these blues is, the bright blue is literal transfer in speech to children, and the dark blue is metaphorical transfer. And it encodes transfer 94% of the time. And in fact, in more recent work, we found that Jabberwocky sentences with no open clause words, so things like she jorped him the fap, primes high-frequency associates like the word give, it primes low-frequency associates like handed, and it also primes semantically related non-associates, that is, verbs that are semantically related to the meaning but don't actually occur often in the construction, like transferred. How does this matter? Because when you're using the verb give, you already know that transfer is involved. Well, notice that there's a slight difference in meaning between Joe baked Sam a cake, which is an instance of the double object construction, and Joe baked a cake for Sam. The second one only can be used when Joe is baking a cake instead of Sam. You wouldn't say Joe baked Sam a cake in this context. You also wouldn't say Joe baked Sam a cake if Joe intends to throw the cake at Sam. Okay, and you see these subtle differences in different constructions. Whenever a verb has a choice between two constructions, there's a difference in function. So it would be fine to welcome someone at a wedding by saying, welcome Joe, who just married into the family, but it means something very different to say, welcome Joe, who married his way into the family. So Humboldt long ago observed that natural language is a means to allow infinite use of finite means. And so one way to understand this on a constructionist approach is that the constructions have open slots, and the slots can be of different sizes, including sentential slots. So in English, the verb is often a very open slot. We can say very creative things like, I grabbed the guy by the collar of his flowered shirt, popped him a punch. Or a 15-year-old Googled his way to revolutionizing cancer detection. Or Mike couldn't believe she had managed to flirt his wallet open again. We find frequent verbs occurring in a multitude of different constructions with slightly different interpretations depending on the construction involved. So these are some examples with sneeze. Each one of these involves a slightly different interpretation. And in English, of course, we can use nouns as verbs. So we can say, I'm going to go Benadryl myself to sleep, or he out-trumped himself. Or my favorite, few people want to be memorialized umming, you knowing, and remember that time when we got drunking their way into infamy. Okay, so English is particularly productive in what kinds of verbs can occur in the slot of these constructions. But at the same time, speakers are not wholly productive in their use of constructions. There are odd gaps in what native speakers find natural. So it's odd to say she explained him the story, or he vanished the rabbit, or the asleep boy. And none of these is due to system-wide constraints in the language, as you can tell by looking at similar cases that have similar meaning or similar phonology. And these are acceptable. So explain is odd in the double object, but tell is fine, and guarantee is fine. Okay, and that's true with all of these cases. Okay, now we know that kids don't reliably get feedback from their caregivers. So if a child says, "Me loves you, mommy," it would be an unusual parent who would slap the kid and correct their grammar. And conversely, if a child produced in perfectly grammatical English, I have just completed a colorful mural on my bedroom wall with indelible markers, the parent is not likely to give them a hug. That is, we're more interested in children's content than in their forms. So we'll get rid of that idea. Okay, so how are construction generalizations constrained? And the idea that I've been working with for a while is that they're statistically preempted. The idea is that people learn to avoid certain grammatical possibilities by systematically witnessing a competing alternative. So we know this is the case for words, and the constructionist approach draws strong parallels between what we know about words and these phrasal constructions. So, and I do think that the same kind of approach carries over very nicely. That is, if you're in a situation like this, and you might expect to hear one of two things. You might expect to hear the magician made the rabbit disappear, or the simple transitive, the magician disappeared the rabbit. But native speakers don't actually say the second one very often, so you're much more likely to hear the magician made the rabbit disappear, the periphrastic causative. And upon hearing that, if both of the other representations were partially active, you're likely to strengthen the periphrastic and weaken the causative. Okay, so let's apply this to a particular case. So one of the odd constraints that I mentioned is the fact that certain adjectives that begin with an unstressed schwa, like asleep, don't sound natural before nouns. So it's odd to say the asleep child. And again, it's fine to say the sleeping child or the astute child. So it's not strictly semantics or phonology. And they're actually a class of adjectives that all resist appearing before nouns in attributive use. There's a historical motivation for this. So here's my nod to language evolution. So in Old English, these a adjectives used to be prepositional phrases. So asleep came from, in Old English, in sleep. And because it was used frequently, it became reduced, and it ultimately became one word that's now reanalyzed as an adjective. When they were prepositions, it made sense that they couldn't occur before nouns, because we don't use prepositions before nouns. We wouldn't say the on drugs man. Interestingly, not all of the a adjectives were prepositional phrases. So afraid didn't come from on frayed. Instead, afraid was a past participle of a verb. But speakers seem to have generalized the restriction to include afraid into the category. So what this means is that synchronically, of course, most of us know the history of the language, and if we did, we wouldn't use it in our speech. It requires that speakers have to keep track of how adjectives have been used. And luckily, this isn't big news to this particular audience, the idea that you're keeping track of how words are used. But what I want to emphasize is that you're keeping track of how words are used in particular constructions. So in a production study with Jeremy Boyd, we asked two questions. One is, would novel a adjectives, could we see this process of including a new a adjective in the category of a adjectives with a new nonsense word? And we also tested the idea of statistical preemption. So the experiment was very simple. People saw two animals like this, two foxes. They were labeled dead and alive. One of them moved to the star. I know it doesn't look very dead, but the screen went blank, and then we simply asked people which fox moved to the star. And we had four conditions. In one condition, we used real a adjectives like asleep. In another, we used near synonyms like sleepy. In another, we used nonsense a adjectives like a feck, and we pronounced them for people. And in the last one, we used nonsense non-a adjectives. We also included fillers because you can imagine in a production study, particularly, people would be very likely to be primed. But it turns out that if you use prototypical adjectives, people overwhelmingly produce the attributive prenominal use because it's a contrastive context. And if you use and we also included examples where the animals were labeled with present tense verbs because you can't say the camp's cow moved to the star. So you have to use a relative clause that is the preemptive context, like the cow that camps, moved to the star. Okay. So we gave them 6 practice trials to explain that we wanted them to use full sentences, but none of the practice trials didn't bias them in one way or another. I mention them just because I'm going to come back to them in the second experiment. Okay. So we can see that, in fact, the judgments are verified. People do avoid using adjectives prenominally, even in a contrastive context. So asleep avoids the prenominal use. The y-axis is the number of prenominal uses, much more than its near synonym sleepy. Interestingly, this was also true of affect, the nonsense adjective. So it was assimilated to the category to some extent. But if you're looking at the y-axis, you might notice that here's the data all at once. There's an interaction. So the effect is much stronger for the real adjectives than for the nonsense adjectives. Okay, so in a second study, we wanted to test this idea of statistical preemption. So we simply introduced that in the pre-exposure blocks. So now we'd show people examples like this, Zeki and affect, and then we'd say, so for example, here you might say the fox that's affect moved to the star. Again, we included 6 practice trials. Again, they weren't overall biased toward the relative clause, so there were also instances of prenominal use. 2 of the novel adjectives, though, were witnessed in a preempting context, 2 out of 4 of the novel adjectives. So remember what we saw in experiment 1? It looked like this. In the second experiment with this minimal preemptive exposure, people's productions are like this, and the interaction disappears. That is, affect and asleep behave the same way. Thank you so much, Ted. I'm so sorry.
My fault.
Okay, no. Okay, oh, that's much better. Thank you, guys. You're great. Thank you so much. Ooh, this is cold. Wonderful.
Mine's fresh.
And if you take a look within the category of nonsense adjectives and look at the ones that had been preempted versus the ones that hadn't been preempted, there's actually very little difference. That is, people assimilated the restriction. So upon witnessing 2 of the nonsense adjectives in a preemptive context, they assimilated all the novel adjectives in this experimental context to the category. Now, there was recently a critique of the idea of statistical preemption. Charles Yang did a corpus analysis of input to children. He looked at about a year's worth of data that was spoken to children before they were 3 years old, and found that there wasn't enough preemptive exposure for kids to learn this adjective restriction. But it turns out, oh, I didn't mean to leave that on that one, sorry. That was rude. Well, it turns out that a senior thesis student at Princeton did a study like the first study with the adjectives, and it turns out that kids don't actually know this restriction until they're about 10 years old. So they do need a lot of time before they learn this restriction on adjectives. Okay. So it's useful to look at naturalistic contexts, and adjectives are, a real example with a restriction. But we know that the adjective restriction already exists for English-speaking adults, and so maybe that made the preemptive exposure work especially well. So I'm going to turn our attention to artificial language studies, and I want to introduce them by recalling a classic study by Wanacott, Newport, and Tannenhouse, where they introduced learners to 2 constructions that had different word orders. So one construction was the VAP construction, so verb, agent, patient, and the other one was verb, patient, agent with a little marker on the agent, ka, verb, patient, agent. They gave different groups of learners different kinds of exposure. So in the lexical input condition, none of the verbs in the input alternated. And then they found in a production task that people showed completely conservative behavior. That is, they used the verbs exactly how they had been witnessed in those same constructions. When a third of the verbs alternated during exposure, people were minimally productive, but they still showed a strong lexical bias. Only when all of the verbs alternated in the input did people show productive behavior. But recall that in natural languages, every construction has its own ecological niche. So we've been working with novel construction learning studies, and the difference between those and artificial language learning is that we expose learners to pairings of novel form and novel meaning. So we create some abstract meaning and associate it with the construction. Okay, so I'm going to tell you about two studies. The first one, and it's going to be consistently labeled in red, APV. The P is bold-faced because here's the scene, P is the patient. The patient is strongly affected. Let me just show you that one more time in case you blinked. Okay. And in the other construction, PAV, the agent is not, the patient is not particularly affected, but the action is the same. Okay. So we had different characters and different actions, different novel verbs, and they were all counterbalanced. Okay, so in what follows, I'm going to be reminding you of that strong effect on the patient with this with this rectangle, showing the big effect, the strong effect, and I'll be reminding you of the small effect with this square. Okay, so in this experiment, we gave people 2 days of exposure. It takes some time to learn 2 different novel constructions. So they just saw 36 sentence scene pairs, each verb used 6 times, and participants were asked to repeat each sentence. We had 2 input conditions. One was a lexical condition in which people saw 3 verbs only in one construction and 3 verbs only in the other construction. And we had a partially alternating condition where 2 out of the 6 verbs were seen in both, with correspondingly different interpretations. And then we gave them both production and sentence rating tasks. I'm only going to show you the production task, but the sentence ratings tasks are completely consistent in their findings. But in the production task, we asked people to describe new scenes, and in some cases, we provided novel new verbs, or new novel verbs. Okay, and we interspersed these with a distractor tasks to avoid priming. So we gave them vocabulary questions, forced choice, sentence comprehension. So the lexical condition then looked like this. Remember, each construction has its own function. So APV has a strong effect, PAV has a weak effect. In the alternating condition, the constructions stay the same. 2 verbs occur in both constructions, though. Okay, so again, here's another production trial. Okay, and people were asked simply what happened here, and the verb was provided. And so they could use one of the 2 constructions. Okay, what we find is that participants recognize the distinct functions of the 2 constructions, and they use verbs in semantically congruent constructions. So here's what it's going to look like. On the y-axis is proportion of congruent responses in red and congruent responses of the PAV in blue. So if we look at novel verbs where there was no previous input, they're all novel verbs, but these are new novel verbs. What you can see is that the scene has a strong impact. So if you cut this box down the middle, you can't flip it over. It's different on both sides because the context is playing a strong role in the productions. People are producing the small effect scenes in the small effect construction and the strong effect scenes in the strong effect construction. But what happens when they had some input? Well, it turns out in the alternating case, even though only 2 out of 6 of the verbs alternated, people are completely productive. They overlook the statistics in the input, the verb-specific statistics in the input. This is different from what Wanacott found, where she found if 1/3 of the verbs alternated, you only got minimal productivity. What about in the lexical condition in which none of the verbs were witnessed alternating? Here again, you see a strong effect of context. But you also see some lexical effect. That is, these are the PAV only verbs, and there's more blue in that box. And these are the strong red verbs, and there's more red in this box. Nonetheless, you get a main effect of effect, although, again, it is stronger in the alternating condition. Okay, so participants generalize novel constructions in contextually appropriate ways. There's a tendency to ignore verb-specific input to better express the intended message. Alternating verbs do promote productivity, But you get, in this experiment, full generalization even when only a third of the verbs alternate. And we've done this with other meanings of the construction. So we've published a different study with information structure properties associated with the construction. And again, we find very parallel results. We did this one. Okay. Oh, good. Okay, I can slow down. So we did this study because if the constructions differ in terms of information structure, people might have a prior tendency to understand that information structure is not usually conditioned by verbs. Okay. So again, we want to ask about statistical preemption. So do you get statistical preemption if you don't have prior knowledge that there is a restriction? So this was the exposure in the lexilus condition, where you did see generalization, remember. We're going to look at something that's very similar to this. So so far it's identical to what the lexical exposure was, 3 verbs in the strong effect construction and 3 verbs in the weak effect construction. But one of those verbs was witnessed in both constructions. And the idea is that this is the preemptive exposure because this verb was witnessed appearing in this construction even with the other, this verb was witnessed in the weak construction even though the context was a strong effect. Okay. Once again, people were able to learn the function of the 2 constructions. So with new novel verbs, they show the same pattern they had showed before. They use these new novel verbs in ways that are congruent with the construction. The preempted verb is successfully preempted, so it only occurred in the blue construction, and you see that it was almost always produced in the blue only construction. Interestingly, other verbs were also used fairly conservatively. So there's more red for the red verbs, and there's more blue for the blue verbs. Okay, although you do see an overall tendency to also obey the construction. Okay, boy, I thought I often give this talk in an hour, but I was trying to talk really fast, and despite the crunch that Steve told us about yesterday. So I'm going to give you the big picture, and then I'm happy to answer questions. You probably have a lot because I only gave you sort of the tip of the iceberg of this kind of approach to language. But the idea is that language users learn pairings of form and function, that is constructions, beyond the level of words. And we do that in every language, although in English, these argument structure patterns are particularly productive. We do this by recording how particular constructions have been used, and that involves noting the contextual information associated with the scenes involved. The exemplars that we witness have to cluster in a very high dimensional similarity space, allowing for generalizations to emerge. So that is, we talk about everything. Word meaning can cover every topic that we can talk about, and we have to situate those word labels with that kind of contextual information. We have to associate constructions with discourse properties, with meanings, with attitudes. We have to learn how each construction is used in our language. We use constructions productively in order to better suit our intended message. So that's when we get creative, when there's no conventional way to express what we want to express, we get creative. We restrict productivity via this error-driven learning, which I'm calling statistical preemption. So if we expect something else, but we hear the canonical form, we get an error signal, and that leads us to strengthen the conventional formulation and weaken the novel formulation. And interestingly, the restrictions themselves can be generalized. So we don't need to see evidence of every single case if the group forms a cluster. We can generalize. And again, if you think about words, none of this is new. We know this about words and how they are regular and irregular. So we know we can generalize restrictions on novel verbs as well. Okay, I want to thank especially my collaborators, Florent Perec on the second set of experiments and Jeremy Boyd on the first, and also, of course, all my lab. And thank you again for getting out in the morning.
minutes for questions. We said tenured people here, non-tenured there.
That was a great talk. Thanks, Adele. I was just wondering, in the very last few minutes of your talk, about how our language system, or the mind in general, deals with incongruency of constructions used in an appropriate context. Because on the one hand, you could argue that it would elicit the same kind of, like an N400, say, effect in ERPs, where you really can't integrate things easily meaning-wise, or it could be the same kind of thing that elicits these very domain general, like error correction signals, where you're like, okay, they just haven't quite learned the form. Do we know anything about that?
That's a really good question. And I'd love to do that experiment. We do have some behavioral studies with, so we've created novel sentences, and some of them have a readily available alternative, and some of them don't. And we find that so there's a difference in judgments. People disprefer the novel sentences where there is some more natural way to say it. And I expect, in general, if there's a more natural way to say it, you should get a P600, right? Because you would see an error and fix it. But if there is no other way to say it, and you need to use this, I bet then you might get an N400, right? Because it's novel. Yeah. Thanks, Ev. Josh.
Hi, Adele. Oh,
Hey.
Josh Hartshorn, Boston College. So that was really neat talk. I really enjoyed the last experiment, just set of experiments. I want to put in a plug. Melissa Klein and Jesse Snedeker are putting together a repository of stimuli, videos of events. If you have not already submitted those events, I really hope you will.
Absolutely. I didn't know about that. Terrific. Yeah, it'd be great to share events.
But the question that I wanted to ask was about the psychological status of statistical preemption and its arch nemesis entrenchment. Which is, I totally believe in the phenomenon. One of the things that stands out is that both of them seem to be in aspects of what you would get from Bayesian inference, right? So if you have a prior for simplicity on your grammar, then anytime you see one thing, that makes everything else less likely.
That's right.
Right. And so my question is, are we really just labeling something that is really Bayesian inference, or is this potentially or are these stories on different MAR levels where, Bayesian inference is the right sort of descriptive theory, but preemption and entrenchment, which might be a little bit simpler to calculate in real time, are the actual algorithmic and real time story of how the learning happens, or none of the above?
Okay, great question. So just for those of you who aren't up on the fiery debate, entrenchment is the idea that you only use what you've heard, and the more you've heard it, the more conservative you are with it. And preemption is different. It makes similar predictions, but the difference is that you don't have to be conservative. You can be creative if you have something new to say. So that is, you are preempted not by something that's more frequent overall, but something that's more frequent and conveys the same message. So the context is really important. To date, so Ben Ombridge is the one who has promoted the entrenchment idea most strongly, and we recently collaborated, and he redid the analyses of those papers, and because of the way they were coded, he's actually coming down in favor of preemption too. Let me just explain, and actually, I have a postdoc, Libby Barak, who has a Bayesian model that involves preemption as a side effect, right? Because you get you're deciding between two clusters, and you want to look for the best fit. Well, so the fit has to be relevant, right? And the size of the cluster matters too. But if you've said something else more frequently, but it doesn't mean the same thing, it doesn't matter, right? So let me just give you a quick, I always ask myself, what would words do? And that always gives me a good intuition. So we know that, for instance, ran preempts run, right? There's really no question about it. Now, there are other verbs that are more frequent. Say we never, we didn't hear ran, we heard walked a lot. Much more frequent, or go. We heard went, so let's say went. We heard went many, many more times. But it doesn't preempt run, right? It's not relevant because it doesn't express the same meaning. Now, again, constructions don't, one little caveat here, and this is why people haven't applied preemption to phrasal forms. they don't mean exactly the same thing, right? I made a big deal of that in the beginning, in fact. They don't mean the same thing. And so Pinker, for example, suggested at one point that preemption might work, but then he dismissed it because of that fact that constructions encode different meanings. But that doesn't mean that preemption can't work, because what you have to look for are contexts where one construction would normally be appropriate, but you hear the other anyway, right? You hear it despite the fact that there's some other construction that would be more appropriate. That's when you get the preemptive exposure. Sorry, so offline I could give you a ton more. You know, we have some studies comparing the two, and I do think that context matters. Thanks, Josh. Okay. Oh, yes.
I didn't quite
Whitney,
catch
yes.
is there like, is it okay? Okay. I don't know about these microphones. So I wanted to ask for a clarification on the part about creativity, about creative uses. And it's the thing that I think is particularly interesting about this kind of work is that it's sort of pushing at the question, what is the status of the system, which standardly is called the grammar, with respect to these forces that operate on our behavior and which can be often characterized well in statistical terms. So it seems like when you speak of the creative behavior, you're talking about the kind of case that would traditionally be called violating the grammar or going out of the system in some sense. I don't know if that's aligned with your way of thinking about it, but I wanted to know, what is the nature of that bound for you? Is there a system which is able to say, this is the rule, this is the way to do it, and then is there a notion of crossing the boundary when you sometimes don't do what the system says, that is somehow pushed that way by these statistical forces?
Okay, no, I actually, I'm glad you asked that question, because that's actually not what I meant by being creative. I mean being creative just the way every linguist does, that we use new formulations. So in English, I was giving examples that are obviously creative, like the pop me a punch, or flirt his wallet open. You don't have to have heard it, but those aren't, no, I don't think people would say they're unacceptable, right? They are licensed, but they're not familiar, they're novel.
But, well, okay, I guess I was
So
interested.
do you create a new construction, you mean?
Yeah, does this have a way, this approach have a way to talk about cases where the grammar actually changes, sort of in the spirit of the question of languages being mutable and the system evolves over time?
So you can get that, that kind of effect, but you don't get dramatic changes very often, because in a existing language, you have a means to express almost every idea. So it's, you know, the unique kinds of situations that you have to combine things in new ways. But, you know, you can create new utterances, an infinite number of utterances, by combining constructions in new ways. So, but occasionally you do buck the trends for expressive power. So let me just give you one example. I said you don't say he vanished it, but you, in some situations you can say he disappeared them, right? And we don't say he disappeared the rabbit, we still don't say that. But people innovated, they disappeared them in a political context because it was particularly expressive, right? It laid the responsibility directly on they, right, on the subject argument. You wanted a direct causative. And so it was innovated, and it is used still in that particular context.
Okay, I would just put in a plug that the theory needs to be able to do that in some sense. There needs to be a mechanism.
Dynamic system.
Well, whatever system, the system of grammar needs to be able to step over that boundary somehow. The theory needs a way to explain how that happens. So
How languages change?
Yeah, in particular in the cases where it's...
Okay, well, I would say, yeah, they change as the statistics changes in the language. It can, you know, it slowly changes, usually by adolescence. I mean, there's a lot of work on grammaticalization and constructualization, and I think that's the right approach, right? You're looking for very frequent patterns that get reduced, and then something gets added because of emphasis, and that's how new constructions are born. So it's piecemeal. It's not like a dramatic change overnight.
Okay.
Well, Ev.
Question about, I don't know if we know about this, but like to the extent that people are consistent, is that some people innovate more than others? Do we know if that relates to other kinds of creativity, or if anybody has looked at that?
That's a really good question. Yeah, I'm curious about that, right? Because we have a lot of online judgments, and we could give them personality
Exactly, or-
tests,
yeah.
right? I bet there is some
Yeah.
generalization there. Yeah, yeah. Thanks.
Can you hear me?
Sure.
Yes. So I've been thinking about error-driven learning. So this is a mechanism for, adding a new construction to your grammar or, learning an alternation that maybe wasn't there before. But oftentimes when we hear something that's unexpected, it truly is an error, right? We make performance errors all the time. So how does this fit in with this overall picture of, when something's truly an error and when something we should think about changing how we are using our language?
Okay, good. So it's importantly incremental. It's statistical. So if you hear one person saying, explain me something, it's just that one person saying it. If you continue to hear a context where people say, explain this to me, which is the preferred form for native speakers, continually the to me will get strengthened and the double object version would get weakened. But the more people who start to use it in the double object, the more those statistics will change. And over time, it could be that new generations are exposed to a language in which both are possible.
Yeah, I've got a lot of Italian friends, so I hear a lot of, explain me this. So
Okay, very good, very good.
I hear this a lot, so it's not that I don't hear it. I hear
Good.
it quite frequently, but I have not decided to actually explain you anything.
Okay, very, very good. And there, I want to emphasize this very high dimensional space and the fact that we learn how things are used in contexts. So you know that your non-native speaker friends use this, but it's localized to that context. That's a cluster of usages that you understand. But if a wide variety of people did it, it would become the norm. So we know when we hear something from a dialect because we hear it only in a limited situation. So the work by Kleinschmidt and Jaeger finds something like this for phonology, and I think it transfers over.
So I just wanted to follow up on
Yes.
that because I say give it me a lot because I
Yeah,
just
that-
like people to give me stuff. But, and you just drew a distinction, which is, I'm glad you drew, which is a difference between, say, one person saying it a lot and a whole community of people saying it maybe not so much. What is it that you use to account for what I assume is a difference, where if the community uses it, that's going to now shift me, whereas if I just say give it me a lot, people aren't going to shift?
Okay, good. So we know that's true. Who gave the talk who showed exactly that? I'm having source confusion. Sorry? Sherry. Okay, thank you. Yes, exactly that point was made yesterday. Well, you're looking at like an incredibly complicated system where, again, context is tied to how you're using things. And so, if every person who uses give it me, which isn't standard English, but it is British English, is British, that fact, it is all in English. Give it me? Actually, I looked it up once. It's not preferred, but it's in corpora much more than English. But much more than standard English, sorry. But, I'm sorry, God. Standard American English, I'm sorry. And the real question is, how do we know which dimensions are relevant? And I don't have a good answer to that. Like, how does a kid know that information structure is the thing that's relevant to topicalization and left dislocation, and semantics is more relevant to the cause-motion construction? How do we, and the question is multiplied when you think of word meaning, right? How do kids know that the meaning of breakfast has to do with breakfast? I don't think we have a good theory of how we pick out the right meanings for anything, the right associations with anything, but we track a lot of very specific information. Yeah. Okay, thank you.
Hello, everybody. It's really fantastic to be here. I'm part of this special thread on language evolution. And for me, I'm extremely nervous because this is the first time I speak to this kind of audience. Now, you see there that I'm in an institute of evolutionary biology, although my background is in linguistics and computer science. And my colleagues around me, they all focus on transitions in biology. You know, for example, how salamander species without lungs, they get lungs. Or how cichlid fish, which have these egg spots on their fin, how they get egg spots. Or how a solitary species becomes a collective species, unicellular, multicellular. So all of these things, you know, they're working on how you go from A to B. Now, I think in language evolution research, what we also would like to do, or maybe should do, is think about transitions. That means, for example, how you go from a language without color expressions to one that has it. Or a language without a way to determine the referent of a noun phrase, to language which has articles or some other device for this. Or a language without any way to express argument structure, like with cases or with word order and prepositions, to a language which has case grammar. Or a language, and this is then the real origins, you know, there's no language and there's a primitive language. So this is the kind of thing that we like to do in our group. And today I'm going to talk about how you could go from a language without phrase structure to a language with phrase structure. And basically, we would like it to be recursive. So that means, you know, if you have a sentence like the one at the bottom here, that you have a hierarchical structure like this. And so what is happening here is that the words that semantically belong together are grouped together, like the wooden table. Wooden is not just floating in the sentence. There's a sequence, there's a particular ordering. There's also a pattern in terms of article, adjective, noun, which is applied to many things. And then there's a way, I call that unitizing, you know, that these elements are brought together in a unit that they can be reused in higher level structure. Now, maybe many of you are not historical linguists, but it's not at all the case that languages had phrase structure or elaborate phrase structure. In fact, in English, when we look at the history, we can see that, you know, in Proto-Indo-European, there was just words were much more floating into an utterance without really being part of phrases. And it's only in Proto-Germanic that you get a slot for adjectives, like in black sheep. And then only in Old English you get articles, you know, you get an extra slot for determiners. Only in Middle English you get the peripheral modifiers, like only the black sheep. And if you look at contemporary English, you know, people stuff more and more things into a noun phrase. It becomes bigger and bigger, and now they eat up whole clauses, you know, like in this example there of the what's the point of voting, etc. Okay, so it is a historical, cultural process, and so we are looking at the cultural evolution here. Now, the question is, how can we study these things? And basically, one possibility is that we take an idea from sociology. I don't know whether you know this guy, Thomas Schelling. Is he known in this community? A little bit, yes. Well, he's a sociologist, and he was interested in studying how macroscopic behavior, in particularly, for example, a pattern in a city, how that would result from the behavior of the individuals. And we have a problem like this in language because, you know, we have all these individuals talking to each other without any central control, without any organized structure, or telling everybody how to speak. But nevertheless, we get coherence, we get diversity, we get change, we get variation. So I think these agent-based models, as they are called, were called by Schelling, is a good way to study language evolution. Now, Schelling got the Nobel Prize in Economics for doing this kind of thing, so I thought, why not? You know, you never know. And so this is an example where he, you know, of segregation in New York City. And in Schelling's model, he has a grid with agents as points on this grid. they have local interactions. And so this is only two, like say, Hispanic and English-speaking people. And basically, there's every agent is kind of looking around, and if the agent feels that there are not enough people speaking the same language, he moves to another location. And so shelling starts with the random distribution of these agents. They interact with each other, and after a little while, you see structure emerging. You see a kind of segregation in the population. So we do this kind of thing for agent-based models. And you can, of course, do this in software simulations, in which case every agent would have language capabilities. You know, we would have to build parsing, production system, conceptualization, all these components, and learning, of course. So we give each of these agents all these capacities, and then we let them interact with each other. And just like in the shelling segregation model, at the end of the day, you know, we see what kind of thing comes out. Now, we not only do this in software, but also with real robots, because language is, of course, about the real world, is interacting. So if we think about embodiment or think about perception, you know, then we can study these things also. And so in these agent-based language models, you have population of interacting agents. There's also a population of 4 meaning pairs. You know, every agent has, well, a couple, and sometimes alternatives, right? And so this population is replication in the sense of a 4 meaning pair may be learned by another agent, so it propagates in this population. Or an agent may reuse a 4 meaning pair that it already knew, and so you get, you know, replication, but you also get variation in these populations because of innovation, performance errors, or maybe overgeneralization in learning. Now, important also, you get selection based on success in communication, because the agents get feedback whether they were successful and will adjust their inventory based on that. They need to maintain expressive power, minimize cognitive effort, and also those 4 meaning pairs that will survive are the ones that are learnable, of course, otherwise they would not propagate at all. So you see here a model which is a biological model of replicator dynamics. In other words, it's evolution by selection. It's not natural selection, you know, as in genetic evolution, but it's a, you could say, linguistic selection based on these criteria. So we've done many things here, and some of it has been about color. You know, this is one experiment with 5 agents, and you see their color vocabularies after 1,000 games, and there after 2,500. And you see that in the beginning there's a lot of variation, and progressively these agents will not only settle on the lexicon, but also on the color categories. And the great thing about all these experiments is that we can track everything, you know, the state of each agent and the collective aggregate, just as the agent-based models that sociologists like to make. So there's lots of things here. I just want to make a bit of publicity for 2 posters that will use this methodology for looking at the emergence of grammatical agreement systems. And there's also a poster on the evolution in the German article system. But my talk is going to be about the emergence of recursive hierarchical structure. Now, of course, you're all now on the edge of your chair, because this is assumed to be a defining characteristic, well, at least some people say that, for the uniqueness of language. And there are many issues. One is, what is the neurological basis for handling recursion? There's also the question, is it unique to language or also used in planning or visual recognition? But then there's the question, why human languages use recursion? Because it's not because humans can do it, you know, that it is used for language, right? And then particularly, how is it possible? How is that process? So I'm going to focus only on the latter 2 questions. That means, why is it there, and how could it emerge in a language? In other words, viewed in this agent-based paradigm, what do we have to put in these agents? What is the minimal thing we have to put so that if we turn on the simulation, then after some time we see a recursive grammar. Okay, now, so let's start with the lexical strategy. That's one where there is no grammar. I made here a simple example. So there's a lexicon. I used Spanish words for the lexicon so that you could see the difference with the English, which I use for the meanings. And you have something like a predicate calculus representation here, you know, and verde is associated here with the predicate color green. And this is a variable, and this is the argument. The question mark before the x indicates that it's a variable. Okay, so suppose the speaker sees this kind of scene, you know, similar to the one that the robots were seeing in this earlier experiment, and comes up with a meaning, you know, a description that he wants to convey to a listener. And so the speaker just looks up in the lexicon and spits out the words, you know, in any kind of order, right? There's no grammar here, there's no syntax. They just spit out the words. So he says, cubo, cubo, verde, grande, or maybe verde, grande, cubo, cubo, or something like this. Okay, the listener gets all these words, does a lexicon lookup, and reconstructs the meaning. Notice that these variables here are different from the ones here because, you know, there are two cubes, so we need, all the time, we need new variables for each of the predicates. And now, the listener has two problems, actually. He needs to find out how the things connect. That means which variables are going to refer to the same thing, so which ones are co-referential. And it could, for example, be that x1, x3, and x4 refer to the same. Now, some of you have already seen which object that would be. And x2 would then be left, okay? You can think about that. Or it could be, here is another way, so the dot means they're bound to the same, they're co-referential. So it could be here, x1 and x3 refer to the same, and x2 and x4. Now, the first, and there are other possibilities. The first is the right one because, you know, x1 here is a cube, x3 means color green here, and x4 is big, and indeed this is the big cube. So in this situation, this set of bindings is the most appropriate one in the interpretation. So you see, you know, the lexicon is giving these bits of meaning, and then they have to become connected. And connected means to find out whether they are, the variables are co-referential. Now, okay, now if you don't have a grammar of any sort, then of course you can use the reality and you can look at it to help you find out which of these variables are the same. Now, there are two issues with it. First of all, when you're speaking on the phone, this wouldn't work, right? Because you don't see the situation, so you need to convey more information. But there's also a problem that the semantic interpretation is a combinatorial problem. Because if you start looking at it, you know, you can combine this with this, and this with that, and that with that, and then this with that. So you see, you have a search space of possibilities. This means cognitive effort. What can you do about it? Well, the first step is to do grouping, okay? And we get here the first aspect of our phrase structure grammar. Grouping simply means that all the words that are introducing predicates about the same thing, they are put together, like here. Verde, cubo, grande, they're put together, and cubo, you know, is separate. When you do that, do you win anything? Well, yes, you do. You can actually compute all this, I mean, theoretically. And you see here, this is the lexical strategy, which is not just exponential, but hyper-exponential. That means if this is on a logarithmic scale, you know, and this is the Bell number, which compute the number of all possibilities, you see that it's still exponential on a logarithmic scale, whereas with the grouping, we get still exponential, you know, but at least it's not hyper-exponential. So we are winning something. Can we do more? Yes. Well, one problem is that, you know, I conveniently here put the boundaries of groups. But of course, if you just have the words, like I say, pequeño, verde, esfera, rojo, grande, cubo, you know, you don't know where to cut it off, right? So now you can do something about that by a second step, which we also see in phrase structure, which is sequencing. That means you impose a particular order on the group. And so this order is going to help us find the beginning and the end of the group. You know, it introduces more predictability. Okay, and so this is what's happening here. This is what the listener would get purely from the lexicon. So you see X1, X3, X4, X2, X5, X6. And this is what the listener can get by using these sequences, knowing these sequences. Now, of course, the agent needs to store, you know, sequences in order to do that. And these sequences are called in computational linguistics n-grams. And also, the agents have to agree about a particular ordering, right? Because you could have the ordering verde pequeño esfera, and then somebody else esfera pequeño verde, and we would get, again, an explosion of possibilities. So the agents need a device to, without the central organizer, to still arrive at a shared set of sequences. And this can be done with a mechanism which is lateral inhibition. Maybe you know about this from Kohunen networks, for example, which is that every sequence in the agent has a score. And when the agent is using it and the communication was successful, the listener, pointed to the right object and so on, then the score increases. And the score of competitors, that means other sequences with the same words with a different ordering, their score decreases. And if you use that, then you get the behavior as shown here. This is again from experiments, agent-based models, where you see that after a while, a certain subset of the sequences is going to win. That means that the agents are zooming in actually on an optimal vocabulary, and again we can, well, not vocabulary, a sequence grammar, and we can compute that actually, and we can prove that they will reach that. Does it help? Yes. This is the search space for utterance of 6 words. On the left we see for the grouping strategy, on the right for the sequencing strategy. In the beginning it's roughly the same because here they are learning the sequences, and after a while the population has a clearly smaller search spaces and also less depth in the search spaces. Okay, so we are making progress here. So you see the style of the argument, right? The reason why we have these properties is because they solve computational problems related to semantic interpretation. Now, of course, when you have just n-grams, there's another combinatorial explosion. I mean, you know that Google uses n-grams in automatic translation and so on, and in 2009, they released their database of n-grams for English, which had, at that time, already 4,600,000,000 n-grams. And today, I'm sure it is 10 billion or 20 billion, So this is nice, but okay. So what is the solution? Is to create abstract patterns. And basically, this means that we need a strategy for the agents need a strategy for creating abstract patterns. And so they will initialize patterns. That means create a new pattern when they don't have one yet. So they have a sequence, no pattern for the sequence, they make one. But there's also, we gave these agents the coercion, which is well known in language. That means if like they are Facebooked, and you've never seen Facebook used as a verb, you can say, well, let's make Facebook a verb, and then it will fit. So this is one way in which categories propagate in the population. Or you can introduce, you can relax constraints on patterns so that they fit, and then potentially learn one of these patterns. I can't go into any of the details because the time is ticking. But this is just experiments now where these agents are learning patterns, building patterns, and you see the improvement with respect to an n-gram strategy. They have less of these patterns. They learn them faster. And we also see that the categories, that these agents are building in making these patterns, that they're also converging. So I now come to the final thing, which is that, okay, so these patterns, will lead to a pattern grammar, abstract patterns like article, adjective, noun, let's say. but not yet to the hierarchical structure. So there's a next step is needed to reduce again the number of patterns that are needed. And this, I call it unitizing, because basically what you do is that if there is an abstract pattern, it's not just used as a pattern, but it also creates a new unit that itself can be the element of another pattern. Again, I cannot go into the detail. I mean, there are papers on how all this works, but I just wanted to end with two graphs. This is from experiment where all these things come together. So the grouping, the sequencing, the patterning, and the unitizing. And so this is experiment with a population. These are the language games they are playing here on this axis. Here we see the syntactic and semantic ambiguity, going down, because of course that's the whole purpose of this exercise, is to avoid cognitive effort because of explosions in the search space. We also see that a number of grammatical constructions is increasing. This is showing the alignment of the constructions between those agents. And finally, I want to show this picture here. This is an experiment where we can turn a knob. The knob is to give these agents more and more complexity, meaning complexity, okay? So in phase A, we just give them a unary predicate. Phase 2B, we give them two unary predicates, then a binary relation like in, then, binary relation, but an additional predicate, and so on. And so we can increase the complexity of what they have to express. And then what you see here is this is a single agent that is building or learning new constructions. And this is the population. And we see the communicative success is the red line here. And every time that we increase the complexity of meanings, then of course the communicative success goes down because they have to build grammar in order to cope with it. You see also the black line is the number of constructions, which here is jumping up. And we see the alignment between the agents. And so what we see is that, in the beginning, every time the complexity goes up, we see some activity, new constructions being built. But the magic happens here, because at this point, we did not need to add anything to what I've told you. All these components were enough to see that from here on, once they get to F and G and we can continue to increase complexity, no new grammatical constructions had to be built. In other words, you would get big red ball in box, on table, in kitchen, on floor, So you could start to build more and more embedded, predications which were reflected in embedded hierarchical structures, but no new constructions had to be acquired. Okay, so I think I have to stop. So I will just show some further references. Thank you very much.
Hi. So one of the things that always gets confusing in discussions of recursion, right, is that people oftentimes are talking about somewhat different things. Some people are talking about syntactic recursion purely in terms of the string of words. Other people are talking about semantics. And one of the things I really enjoyed about the talk is that you were very clear, I think, about what you were talking about. You were talking about the recursive syntactic structure, right? Assuming, actually, that the conceptual structure was already implicitly fairly highly organized, right? Arguably even recursive to be able to represent these representations. And so that actually led me to a kind of curious place. I was thinking that you started out assuming a beginning point where there was a critter that had recursive semantic interpretations, but that creature did something very strange. That creature just arbitrarily started outspitting words that linked up to all sorts of different parts of this actually very organized conceptual representation. Even if we just take the simplest case with the two objects up there, that was a creature that kept moving its attention back and forth to different words. it was also a communicative system where different people had managed to converge on some very abstract word meanings without ever having any common structure in place. And I guess while I think you could do this, I just don't imagine why we would ever be such a creature. Everything I know about word learning tells me that you actually need to have a fairly good understanding of the other person's conceptual structures and begin to pick them apart before you can link up the abstract words. So that's not that creature. And everything I know about human attention tells me that why would I switch back and forth between these different reference and outspit words at random? So why would we want to start here?
Okay. Well, first of all, the semantic structure is not recursive. And you don't need to use syntactic structure to communicate it. You could say, there's a block, it is red, it's left of a box, you know. So you could have, and in fact, that's what you see also in languages which almost don't use recursion, is that they cut it up in different parts. So the recursion is not in the semantic structure.
But underlying that, there's some representation that binds all of those features to the same box, right? And if that box is inside of a larger predicate, and that sentence is actually being linked onto something else, right? There's a conceptual representation, for example, in a relative clause, which represents an event inside event.
Yeah, but the process of looking up in the lexicon is also, I mean, not structured in advance, right? There's no fixed ordering to it.
Absolutely.
So the one word may pop up. In fact, we heard several talks about that. That is a word that already, and speech errors that may occur because you've already had a word that's later in the sentence is already popping up, but you should not say it yet because it's not fitting in the syntactic structure. So I would say that there's a kind of parallel lookup process. And the ordering of when the words come in is not necessarily the order in which they're going to be put in the syntactic structure. And so, I don't know, we could talk more, but the main thing is the recursion is not in the semantic structure and it's not necessarily in the syntactic structure. Yeah.
Hi, Richard Futrell from MIT. So when you were motivating the introduction of grouping, it was to reduce this combinatorial explosion in the semantic search space. I'm wondering what motivates grouping at that point as opposed to other strategies such as co-indexation. So why do you choose the particular path of strategies that you do rather than other possible ones?
Well, this is like a theoretical argument, right? You want to think what is the minimal strategy and what does it give you? And so for each of these, we want to be able to calculate theoretically the gain in efficiency and then see what is needed cognitively to make that happen. So that's why, I mean, having a sequence, an ordered sequence, is more complex than just having a group, an ordered group. And so you see also in languages, by the way, that some of them have much less ordering in their sequences, and they use other devices like grammatical agreement. You know, so in Latin, for example, you can have the adjective at the end of the sentence with the noun phrase at the beginning of it. And so this grouping is not a necessary strategy. In fact, grammatical agreement that will be in the posters that I mentioned, you know, is another route to deal with the same sorts of problems, but in a different way.
Thanks.
I think we're going to have to move on. Our next speaker is Laura Lindsay, and she'll be telling us about the development of turn-taking. Preschoolers may predict what they will say, but they don't use those predictions to plan their lives.
I might take. Oh, my computer decided to die. Oh, there we go. So, I am going to come and talk to you about some work I've been doing just recently looking at turn-taking and how the turn-taking system develops in children. that better? Awesome. So, we have been looking at, so as we've been seeing in a couple of talks yesterday, speakers constantly switch between speaking and listening roles. And we're really good at this. In fact, we're really fast. We take about there's about 200 millisecond gap between turns. However, there's a discrepancy in the fact that production processes are really slow, and it takes about 600 milliseconds for us to produce a single content word, and even longer for us to produce a simple utterance. So the question is, how can we explain this discrepancy? Now, one proposal suggests that there's a very important role prediction plays, especially predictions about the content of a term. So in this example, the guy's thinking, the speaker's saying, how can you not like birthdays? Are you not excited at the idea of eating the? And the listener predicts that he's going to end the sentence with the word cake. Now, by doing this, this listener can begin early response planning. So he can start planning his response. No. And there's actually some recent evidence suggesting that this is the case, which Steve Levinson said, showed us yesterday. Now, as well as being able to plan our response, we may also be able to begin predicting when a turn is going to end, so making timing predictions. And one proposal suggests that what we're doing is we're making predictions about the content and using those predictions about the content to estimate how long that turn is going to take. So in this example, the listener is predicting that the word is going to end in cake. He might think that's going to take 400 milliseconds, and then he can begin planning his plan articulation processes and begin speaking at 400 milliseconds. Now, whilst adults are really good at taking turns and being really fast, children are not. So if you can see here, the black curve shows adult-to-adult conversations, and if you look at the mid-grey curve, what we're seeing is the children's responses to to an adult's question, and what they're really slow. So they're actually taking about half a second to respond to the adult, and then there's this big, long distribution towards the end, where they're taking even longer. Now, why is this the case? Because there's evidence to show that children are making predictions about the content of a term, so they're able to say, predict that the speaker is going to finish his sentence with the word cake. And as well as this, they're also able to anticipate when a speaker switch is going to occur. So what Casillas and Frank have shown is when they're watching a conversation of some people having a conversation, their eye gaze moves towards the next speaker before the current speaker has actually finished speaking, suggesting they actually know when someone's going to stop speaking. Now, if they can do this, then what is their difficulty with turn taking due to? So we've come up with a couple of explanations to why this may be the case. So explanation one is that whilst they can make predictions about when a turn is going to end when they're watching a conversation, they actually can't do this whilst they're also preparing a response as well. And this is what we tested in experiment 1. Alternatively, they may be able to make predictions about the content, but they can't use these predictions about content to aid response planning processes. And so therefore, they're slower to respond because they haven't got their response planned already. And this is what we tested in experiment 2. So I'll talk about experiment 1 first. So what we had participants do, we had adults, 3-year-olds and 5-year-olds, play an interactive iPad maze game, where they're helping Peter Pan chase Captain Hook. Now, at crossroads in the maze, each direction of the crossroad would be associated with a character, a different character, and Captain Hook would go and hide behind one of these characters. And Peter Pan would ask a question about where he was, where Captain Hook was, and who he should go past. So I'm just going to show you a video of what this looked like. So as you can see, maybe not quite so clearly because the contrast is really bad, but Peter Pan is going and chasing Captain Hook. At the crossroads, we see that he goes towards the characters, and unfortunately my sound doesn't work, but Peter Pan asks, "Oh look, should we go past Fireman Sam?" And then the participants respond yes or no. And I should mention that this is a spoken response, which is quite different from other studies. And we measured the the response time, or the gap duration between the question offset and the participant's response. Now, our critical prediction in this experiment, so we're looking at how whether participants can make time and predictions based on, whilst also preparing a response, was we predicted an interaction between two factors. So the first factor we predicted was the expectations of what Peter Pan was going to say. So 1/3 of the time, Peter Pan would ask about the incorrect character, and the incorrect character being the character that Captain Hook has not gone past. And 2/3 of the time, Peter Pan asked about the correct character being the correct character being the one that Captain Hook has gone past. And yeah, and we made sure that we had this correct bias by including fillers. What we also manipulated was the expected timing of the term. So in half of the trials, the character name shown had the same length name, and the other half of the time, characters had the different length name. So I'm going to show you what this looked like. So when in the same length conditions, when you're always expecting to hear a short word, regardless of whether the question is expected or unexpected. Therefore, if you're making predictions about timing, there shouldn't be that much of a delay. However, in the different length condition, critically in that when the question is unexpected, you should be expecting to hear a long word, but instead you hear a short word. Now, if you're assuming that you're going to be hearing, hang on. So if you're assuming that, sorry, I've had a proper mind blank. So they should be delayed in responding to this in this condition because they're expecting to hear a long word. They should be ready to begin speaking later because they think they're going to hear a long word. Therefore, we should see a delay in this condition because they've heard a short word. So there is an interaction between, so what we're critically predicting is an interaction between the expected content and the expected timing. Now, what we actually find is no such interaction. Now, in these graphs, we find on the x-axis, we've got the question type, so whether it's expected or unexpected. Black bars represent when the character is the same length name, and grey bars are when the character is a different length name. And on the y-axis, we've got gap duration. And this is for adults, 5-year-olds, and 3-year-olds. And what we find critically is there is no interaction between the expected content and expected timing, suggesting that neither children nor adults are actually making timing predictions when they are answering, when they are also trying to prepare a response in advance. Now, this is very interesting because it, first of all, suggests that timing predictions are not that important when we're actually taking turns. So we can rule out explanation 1. But what about explanation 2, which is suggesting that we're making predictions about the content and using this to guide response planning processes? So we did an exploratory analysis on the data from experiment 1, where we looked at, and what we found was that there is a correlation between the character name length and the gap duration. So participants of all age groups were much faster to respond to the question when the character name was long. And what this suggests, so when they hear the f in fireman Sam, they can begin response planning processes, and therefore when the end of the question comes to an end, so when they hear Sam, they can begin speaking. So what this shows is that whilst participants can begin planning their response early, we still kind of need to make sure that they are using predictions about how an utterance is going to play out to aid response planning. So what we did in experiment 2 was, again, we had participants play a really an interactive iPad maze game as before, but this time they're trying to find an animal in a maze. And so Peter Pan is going again around the maze. When he reaches the character, it stops, it goes into a zoomed-in version, and Peter Pan asks a question about which animal is hiding. No, which character is hiding which animal? Now, what we manipulated in this experiment was the position the critical information appeared in the question. So in half of the questions, participants heard the character name, being the critical information, appeared early in the question. So is Doc McStuffins hiding the parrot? And in the other half of the time, the participants in the other half of the time, the critical information appeared late. So is the parrot behind Doc McStuffins? Now, what we also manipulated was the maze structure. So half of the participants played a one-animal maze, where they're only trying to find one animal, and the other half of the participants played a two-animal maze, where they're trying to find two animals. So I'll show you what this looks like. So in the two-animal maze conditions, it doesn't matter whether the critical information appears early or late. You can never begin response planning processes because you actually don't know how the question is going to pan out. However, in the one-animal maze condition, when the critical information, the character name, appears early, when you get to Doc McStuffins, you know that the Peter Pan is going to be referring to the parrot, so you can begin response planning processes. Therefore, you should be much faster to respond in this condition if you're using predictions about how a question is going to pan out to guide response planning processes. Now, what we found was that adults show this predicted interaction between maze structure and order of mention. So, on the x-axis, we find the maze structure, so one animal and two animal mazes. The black bars are for early questions, and the grey bars are for late questions. And again, gap durations on the y-axis for adults, 5-year-olds, and 3-year-olds. Now, like I say, only adults showed this interaction, and children didn't, which suggested that adults are using predictions about response planning, using predictions to guide response planning processes, but children aren't. And this is where we got to when we submitted our abstract. And what we thought this meant was that children, whilst they can make content predictions and they can plan their responses early, their issue with turn-taking was that they can't combine these two skills together, which is why they're slow to respond. However, we didn't find a higher order interaction between that being that there was no age differences in the interaction term, which is weird. You would think children would be acting differently to adults. So I'm just going to remind you of the distribution that we see in children's response data in the corpora. So as you can see here, adults have got a nice, lovely, clean curve, whereas children's responses are really kind of messy. So they're different from adults. And when you look at our data, it shows a similar pattern, where we've got a nice, clean, lovely adult data, and then children's are just messy. Now, what we did was we fitted an X-Gaussian distribution to our response data and to our response time data. So an X-Gaussian distribution consists of a Gaussian distribution, or a normal distribution, and an exponential distribution. And these different distributions are characterized by different parameters. So in a Gaussian distribution, we've got mu, which is the mean, and sigma, which is the standard deviation. And with an exponential distribution, we have got tau, which is like the rate of the exponential. Now, in the psychological literature, mu has often been thought of as kind of reflecting basic functioning, whereas tau reflects interference effects. So what we did was we hierarchically modeled these parameters by condition, accounting for the variance of subjects and the items. And we jointly estimated these using a Bayesian algorithm. Okay, now what we found. So if we look at mu first. So we found, like in the previous analysis, adults are showing this interaction between maze structure and order of mention. Now, when we looked at the children's data, they're also showing this interaction, which is really, which is different from our previous analysis. Now, I should mention that what we're looking at here is normalized response time distributions. But the fact that the children are showing this interaction on MOO is really, really cool, because what it suggests is that they're actually using predictions about what they're going to hear, and they're using this to guide response planning processes. Now, when we look at tau, oh, and I should mention that there is no higher, this interaction term is not significantly different between adults and children. Now, when we look at tau, as we can see, the adults have got very low values on tau. However, we look at the children's data, which is very expected. There's very large tau values, but what we found was an interaction between the two animal, between maze structure again and order of mention. So children were especially slow in the two animal late conditions, which is the hardest task that they have to actually do. And what this suggests is that when children are taking turns, they are influenced by interference effects. And this may be because of they're still developing executive functions, there may be just too much cognitive load in what's going on. And yeah, so this is really cool. And obviously, the differences in tau are significantly different between adults and children. So, to sum up, what we found in this experiment is that neither children or adults are making timing predictions when they also have to prepare a response in advance. And this is in contrast to some of the literature that is out there. Now, what's also cool is that that children and adults are also preparing the response early, and when we account for the response time distributions, they are also, both children and adults are also using predictions to guide response planning processes. Now, let's try and match this kind of data to the theory. So we heard Steve Levinson talk about his model earlier, and this is a very prominent turn-taking model, suggesting that there is an important role for predictions about what you're going to hear and early preparation. And we have shown this with our data. And there's also an important role for predictions about turn ends. Now, we have shown in our experiments that by the age of 3, children have got the cognitive architecture necessary to begin predicting what they're going to hear about in a speaker's turn, planning their response early, and also combining these two skills together, which is cool. But there doesn't seem to be a very important role, at least in our yes-no questions, for these turn-end predictions. Well, these fine-grained turn-end predictions, I should say. And that's it. I really want to thank you guys for listening. I hope you found it interesting. And I really want to thank Chiara for all her support and Hugh back home, who has been amazing. So thank you.
Hi, Sarah Brown-Schmidt Vanderbilt. This was a lovely presentation. I really enjoyed it.
Thank you.
So the question I had to ask you has to do with your dependent measure.
Okay.
And what it means. So you, at times in the talk, we're talking about precise timing of turn end, like when your partner's going to stop talking.
Yeah.
And at other times you were talking about predicting your own, like what you're going to say next.
Yeah.
And your measurement was like the difference between when the person started talking to answer their question and when the other person stopped talking. So you had some negative values.
Yes.
Right? That could be negative or positive.
Yes.
And it seems like if you're using that kind of dependent measure, it prevents you from asking questions about precision of turn-taking timing, of estimating the ends of turn-taking, because like a negative value is going to make it give you a smaller value on your dependent measure, but in fact, a negative value would be poor timing of
Yeah.
turn-taking responding. And so you end up making some conclusions about precision of turn-taking, but it seems like you're not measuring that. And so, but you have great evidence for timing of your own responses and making predictive planning there, and I thought those arguments were really strong. So I thought I'm asking if you can comment on, why the choice in the dependent measure, and if you could think about that measure in a different way to answer the precision question.
So about that, we actually found very little, the amount of overlaps that children and adults were producing was very small. So whilst we did have some negative responses, that it was like a tiny portion of our data. Can't remember the exact percentages, but it wasn't very much. With regards to the precision of the timing, I'd have to have a think about that.
I think actually this question naturally follows on Sarah's, which is that you are discussing this oftentimes as if it were an active process, that turn-taking behavior is guided by these predictions, right,
Yeah.
that are occurring, and wow, these two systems are coordinated. But I was really tempted to try to think about this passively, and I was wondering what would rule that out, that I have to have a message plan before I can begin working out my utterance. And true, I might hold off on that while you're still talking, right? But all you're measuring is that gap, the degree to which that message planning has gotten to a certain level at the point when the other person has stopped talking so that I can begin talking. There doesn't have to be any active use of this information in term-taking planning, right, to get this behavior. Or I'm missing something.
I guess you're right. Yeah. No. Can you rephrase your question? I'm so sorry.
I can model, let's just pick two little box and arrow models,
Yeah.
right? One box and arrow model is that all I do over here on the turn-taking side is I have a little system that keeps me quiet until you stop talking, and then maybe it has a little delay to start again, or whatever you need over there. Or maybe it waits for your, prosodic information to indicate it's a break, whatever. There's a turn-taking system. It's pretty naive over here, right? But it needs to have a utterance that's gotten to a certain level of planning before it can initiate it all. Over here, what I've got is the kid, right, is a message planning system. And there's delays in this message planning when the information comes late in the utterance, when there's ambiguity, right? And these two things are operating totally separately.
Okay.
Except for the fact that you need to have the message in order to begin, and you need to have a syntactic plan or some level of plan in order to begin speaking. So this would be a case where this is completely a passive effect upon turn-taking, not a turn-taking device that is exquisitely tuned to the information about, ambiguity and predictability.
Okay. I think I'm going to have to think about this.
Okay.
We could talk about this later. Is that okay?
That's totally fine.
I'm sorry. I'm on the spot now, so I'm like, whoa.
Here's an easier question.
Yay!
Chigusa Kurumada, University of Rochester. I was wondering what kind of things participants said. They weren't allowed to say anything, right? I'd assume adults would just say yes or no. But I can imagine a 3-year-old say, no, it was actually blah, blah, blah. Then a 3-year-old had to plan a lot of things to say. So, is there any variability in terms of what they said?
Yeah, so kids were actually saying lots of different things, but most of the time they were saying yes and no. And what we did was we actually didn't include the trials where they were saying lots of different things.
You did include?
I don't think we did we? No.
Okay, so that was
so we kind of controlled for that.
But,
so they were
but I
just
think
yes.
Overall, the construal of the task might have been different across kids and adults, right? Adults knew that the answer had to be just yes or no. They didn't have to plan anything else.
Yeah,
Right,
well, the same
right,
was
so
with the kids because we told them answer yes
but
or answer
it's
no.
really hard to ensure that when you
Well,
work with
yeah,
kids,
this
right?
is true. Kids are noisy.
Well, no,
they're
that's not what I'm
messy.
saying, but that's kind of like an interesting thing, right?
Well,
when
yeah,
you just
this-
look at overall turn-taking systems in kids and adults, they may be just construing the situation, construing the task of conversation differently. So that's sort of the point of the question, but yeah, you control the types of answers, in this particular analysis. Okay,
cool.
Thanks.
I'm hoping you won't have to think too much for this one. I just want to ask a sort of factual question about the data. So when dealing with this kind of distributional data, it's hard to know whether, when you have this kind of effect in tau, essentially in the tail, and you're looking at individual responses, one possibility is to say, oh, well, there's noise, and we're seeing this emerge there on responses within an individual. So the question I have is, are there specific individuals who tend to be out in that tail, or is it responses within individuals that tend to be out in that tail? Have you looked at how these distributions follow the individual children and looked at individual differences?
Okay, I'm going to be honest here. I am not the forefront of this distributional analysis work. So I feel like I'm not sure, but I can ask my, Chiara might be able to answer this, or...
The answer is that we haven't looked at that specifically, but because the way the parameters are estimated takes into account both participant and item variance, I would assume that any effect we see is over and beyond.
Yep.
Jerry, could you repeat the answer? Oh, sorry. So
So basically, we didn't look at that specifically, but because the parameters are estimated taking into account by participant and by item variance, I would assume that any effect we see is over and beyond, like, particularly slow individuals or particularly slow trials.
Do you think there's any influence of the fact that the turn taking here was with a non-human, right? It's with Peter Pan, isn't it?
Yeah.
So, I mean, this is just an intuition on my part, but I don't feel like I have to really obey all the rules of turn taking with Peter Pan in an iPad game the way I do with individuals, where there's social conventions about, you know, how quickly you should jump into a turn or how much time you should wait. And so I'm just wondering whether, you know, some of the differences between the adults and the children in your first analyses may just be that, you know, that the rules of the game are slightly different here for our turn taking, and it may take children longer to kind of figure out the social conventions of turn taking. It might not be all about planning, it may just be about social appropriateness in some sense.
Well, this is true, but I think in this experiment what we were trying to say is kind of get rid of this social appropriateness and look mainly at the how they're responding when it comes to like actual linguistic evidence only. Does that make sense?
It makes sense. I'm just feeling like what you're trying to do is model what kids are doing in the wild.
Yeah?
By doing something that they don't do in the wild. You don't have to
Yeah.
answer that right now. It's just something to think about.
That's cool.
Yeah, that's fine. Let's go to the speaker.
Oh, thank you. I feel like they asked me a question.
Coffee break. Back at 11. Be back at 11.
Hi. Oh, thank you.
Getting the question line, so I just didn't. But I was really interested in...
Everybody's been there. They just say, and you're just too honest, you know, you just say, you know, Laura, answer this, you know. But everybody's been there. Yeah, you did a good job.
You handled
Thank
it
you so much. This is my first ever talk.
Really?
Yes.
Oh, you did great.
Oh, thank you.
And also, you've given the hardest talk ever in your career, and everything else been a little bit easier. Like, it's fine. I have, like, yeah, no, it's...
You got great questions,
Those
and
were-
you handled them like a princess, so really nice.
No, these were like top questions. So I was really interested in analyses that were doing to kind of separate these responses into these distributions. And what I liked about it is that it seems like that should generate some reasonably specific questions about kids' behavior if you're able to sort of control the other distributions. And so if you can sort of lower their general processing level using their hits rates.
I'm just checking the thing to see that it's...
So, like, I just think it's really cool place to find yourself. Not a fantastic place to find yourself. Like, I think it'd be really cool to try to find out, like, if it is actually the case that the behavior you're seeing in the kids is about this increasing and increasing interference. What I had is, when you're thinking about fitting these models, and you've got individual variation, Are you thinking about like the most interfering kids as having like very, very long tails? Or are you thinking about having like a stronger mixture of its distribution? Like how do you think about individual variation? I can't decide if this
So which one do I? Okay, next. So this is there a port like this? No. What about on the other side? Yes. Yes? You should be able to connect straight to the thing. Oops. Oh. Here. So it was this. Maybe this one. So. Okay. That's right. Yeah. There's so many different stupid connections now. Okay, this works. Does it show? I just want to make sure that I can see my comments.
Yeah.
That's the.
So I work.
No, but I can't. So there's like this center view.
So she just asked to the answer. Like it can feel like very adversarial, but like a lot of this is
For all of it, I'm just going to say the first thing.
Yeah, that's right. Like,
that's what you get. So you get to.
Che la nota la vera qualche.
So I think should ask you questions basically about like how much energy contributed by the child's organic planning versus the child's start plan, right? It's like are you planning the speech act or are you planning the initiation of the speech act, right? Yeah. I mean that's what I was thinking is the data.
Okay. All right. Okay. This.
Cool.
Good. So
what is?
Can I leave
Sorry,
this
what
here?
is the thing you just took off? I think I might need that.
You might need that.
Yeah.
Okay.
Wait, but you have a Mac? I think if you have a Mac, you might need this one.
That one.
Yeah.
And that's why.
What?
No, this one you also need to read.
Huh. Okay.
So you need this one. I'm going to leave this one right at the right here, but in any case, I'll.
Yeah, that would be really good. I'm also going to leave my pointer.
Good. Okay. We'll put all the stuff we need on the right.
So crisis solved.
Yes. Good. I'm glad.
Yeah, me too.
Me too.
So are you say the title of our talk? Because I've been practicing it with it.
I'm going to say that the name of the first author and the title of the talk.
Okay, I might repeat that. Just
That's
because
all up
I'm
to you.
already kind of like automatic zone. Okay.
People have very strong opinions about like reporters for this kind of research.
we've got to start somewhere. So it's the first step.
Okay, so we'll just leave it plugged in. Yeah.
Or for data or
Good.
So we're actually thinking of a big step here.
Okay. Let's put them in order then, just so we know.
Right. Okay. I'll get the charger.
Perfect.
Okay, so
Do I need to? Do you want me to leave this on, or what the other people want to leave?
let's see. There's one more person I think who needs
Yeah.
to test. Let me
No,
make
it's
sure.
I'm first, yeah.
But it wasn't really my stuff, and like I would think about this as very appropriate.
Yeah.
I did it. All the answers. And my mind went.
So we've got first, second,
Thank you.
third, and then where's Adam? It's always awful, yeah, but it'll be great.
Yeah, it'll be great. It's not like one computer and people sit there.
Sometimes they try that too, but then, different people finish their talks at different points in time, including like half an hour before they're supposed to give a talk, and then...
And I was walking
wandering off in the snow. Harry can go to the bathroom real quick, but if Adam shows up, maybe he can also try to...
Is that the ice, the water?
Yes, that, the water is fun. Very nice. I love this little queue of laptops here. This is looking great.
Yeah. Okay. Whose is this? I'm drinking this one.
Yeah, no, we have more. Okay, there we go. That's why there's. So we're starting a little late.
Yeah, it's already 5 minutes.
Get people, you have 30 minutes total. Make sure it's whatever we started at. As opposed to try to.
That is like customer service, right? You're like, it's not just fancy at all.
Okay.
Thank you for putting this
I'm just going to announce it here.
Okay.
They're coming. So it's 11:04.
11:04.
Clock up there.
Oh, yeah. I was looking for a round thing with hands.
All right, how are you?
Okay, let me just announce.
Okay. Yeah. We do just are we about the same height? I'm sure.
Yeah. Have you tried yours? Okay. Okay, but it all. Okay, cool.
Great.
There's always a great question, right?
Where's Jesse too?
What signs do you have? You have 10 minutes to
So you're going to get 2 minutes. Yeah. Because you're in a 15-minute slot.
I'm in 15
Yeah.
minutes. It's going to probably going to have some more.
Okay, yeah.
You're having another.
Yeah, I'll give you 2 minutes. Okay. Okay. All right, our first speaker of the session is Ming Xiang, who will deliver a talk entitled Production Bias, but Not Parsing Complexity Predicts WH Scope Comprehension Preferences.
Okay, can everybody hear me? Okay. Okay, I'm going to talk about WH dependencies today. So WH dependencies, like this example demonstrates here, important to study because understanding the relationship between a dislocated WH element and its base position provides a good opportunity for us to understanding the mechanisms that support rapid and sophisticated structure building in sentence comprehension. There's a large literature on this topic already. And today I'm going to look at different kinds of WH construction, WH in situ. So this is typologically very common actually, but received relatively less attention in processing. So here's an example from Mandarin Chinese. So you can see the WH word which city stays in its canonical argument position. There's no dislocation of that argument on the surface string, but it receives exactly the same interpretation as its English counterpart. All right, so even though there's no dislocation of the WH element on the surface string, I'm going to, at the outset, make a fairly standard syntactic semantic assumption about representations that the comprehender may need to construct in their mental representation. So that is, there is this so-called covert or silent dependency between the in situ WH element and its scope position. So by scope, I simply means that for the WH word to be interpreted semantically, it needs to be associated with a clause. So in this particular example, if you associate the WH word which city with this embedded clause, that is, the scope is at the left edge of the embedded clause, you're going to interpret it as an embedded question. But if you associate the WH with the matrix clause, the left edge of the whole sentence, you're going to interpret it as a matrix question. And in this particular case, the period, the punctuation mark, does help you to disambiguate, but if you don't have that, the sentence will be ambiguous. Okay? So, the notations I'm using, just CP indicates a clause, plus Q simply means this is a question, so it's an interrogative clause, right? So there's a long list of linguistic arguments that have been put forward to support this idea that you need something like a silent dependency in the semantic or syntactic representation. And we actually have, from our own work, we have some previous work using or made a processing argument that suggests that for Chinese speakers, when they comprehend a WH in situ construction, it does look like they are constructing some sort of silent dependency. In particularly, while encountering a WH in situ element, it looks like they need to retrieve the correct scope position, and the memory retrieval is subject to the same kind of constraints as the dependency formation for overt dependencies. For example, we can observe similarity-based memory interference effect and so on. So I can talk more about this if you're interested. So in today's talk, I'm going to make two empirical observations. So in the first half of the talk, in the experiment 1 and 2, we're going to ask the question about, while constructing this silent dependency, whether we observe a locality bias, just like the dependency formation for overt dependencies. And to preview what we find, we're going to show that there is actually a locality bias, such that shorter dependencies are easier to process incrementally. And after that, I'm going to probe the question as how people actually interpret these scope. So you may think that because there's a locality bias in parsing, people prefer shorter dependency when they trying to identify the scope position. You may predict that people also prefer the local scope interpretation. But surprisingly, I'm going to show you data that it turns out longer dependency is actually ultimately preferred for scope interpretation. So this poses a contrast or surprising discrepancy between incremental structure building and global interpretation. And the global interpretation preference turns out to match the production preference pretty well. Okay, so let me start to probe this question about locality. To understand whether there's a locality bias, we manipulated a construction like this. So schematically speaking, there is a WH in situ element here that stays at the end of the sentence. Then there are two verbs that introduce two embedded clauses. So the CP1 and CP2 here are the two embedded clauses. So they introduce two potential scope positions. So this construction could be potentially ambiguous in terms of its scope interpretation. So we are asking the question whether the local scope, the CP2 one, is actually the easier to access for the parser. Okay? To get at that question, we made use of a lexical semantic or lexical difference between two kinds of verbs. So one kind of verb is like know. So know is a verb that can take an embedded question. So you can say John knew, which meant the police protected. A different kind of verbs like believe, it cannot take embedded question. So John believed, which meant the police protected. So that's ungrammatical. So the same distinction holds in Mandarin Chinese. So that's critical in our manipulation. So keeping that distinction in mind, we created two conditions like this. So on the top condition, so the lower verb is no, so that means there is a local dependency that's possible, so there's a local interrogative clause that's possible. The bottom condition with the second verb believe is going to block that local dependency, okay? So at this point, let me just be clear about what we would expect, or one kind of expectation under the assumption that there is locality bias is that if people somehow access the local scope faster or easier, then when the local scope is blocked, like in the bottom condition, we predict processing difficulty. Okay? So also keep in mind that under this setup, the top condition is actually globally ambiguous because both scope interpretations are possible. And the bottom condition is not ambiguous, only one scope interpretation is possible. Okay? So I will come back to that in a moment. So we did an eye tracking study, so people read these sentences and while their eye movements are measured, and the task is a binary acceptability judgment task. They just judge whether these sentences are acceptable or not. So here is an example, just for people who read Chinese. So here's the result. So on the left, sorry, if you want to see that again, I'll show you later. So here is the acceptability judgment on the left. So you can see that acceptability-wise, when the local verb is believe, that's the gray bar, the acceptability is much lower than the light blue bar when the local verb is no, okay? And on the right, the reading time reflects that, replicates that result as well. So if you look at the regression past reading time on the in situ WH phrase, so basically the last word in the sentence, you see that the local verb is believe, then there's much longer reading time than when the local verb is no, okay? So given these results, on the one hand, you can say it does support our initial hypothesis that when the local dependency is blocked, the sentence becomes much harder to process. And on the other hand, you may ask whether the results can be explained due to, not due to dependency formation per se, but due to ambiguity resolution. So there was this talk by Brian Dillon and colleague on Friday talking about ambiguity advantage. And in our stimuli, it's true when the local dependency is possible, that sentence is also ambiguous, and that's the easier sentence to process. So we want to rule out that possibility, whether it's actually due to ambiguity advantage. So to rule out that possibility, the next experiment will simply swap the position between the two verbs. So now the top condition is still ambiguous, nothing changed. The bottom condition now is different, so it's still unambiguous, but now the local verb is actually one that can give you a good local dependency, but the top verb now is believe, so that blocked the higher dependency. So when you look at these two conditions, you see that, so now the new data, both the acceptability and the reading time data are in black and the dark blue. So you can see that the difference between two conditions disappeared, and in contrast to the light gray and the light blue bars I just showed you earlier, okay? So to summarize the findings, basically, the cut is not between whether a sentence is ambiguous or not. It's true when the sentence is ambiguous, both sentences are relatively easy, but when the sentence is unambiguous, the sentence could also be easy as long as the local dependency is possible. So the only case when the sentence is very hard is when the local verb is believe, that blocks a local dependency, okay? So given that evidence, we think this suggests that the shorter covert dependency between the local scope position and in situ WH is more easily accessed. And then there will be greater processing difficulty if the local dependency is blocked. So there are maybe a number of different ways that can model this effect, and one straightforward way is to model this in terms of memory retrieval and memory decay, and the assumption that when encountered an in situ WH, the comprehender would trigger this memory retrieval process. And if you're interested, we can talk more about that in the question period. But in the rest of my time, I want to switch gear and ask about the interpretation question. So the data I've shown you, they are obtained from acceptability judgments. So we know how difficult or hard for people to construct a dependency and to make judgment about whether this is acceptable or not. But we actually don't have direct evidence about how people actually interpreted these constructions. So given a construction like this, there are two possible scope positions. And we wonder which scope interpretation is the preferred interpretation. And as I said, given the locality bias, and I just showed you, it seems to be a simple prediction that people will also prefer the local scope interpretation. And to get some data on that question, we did a choose value judgment task. So in this task, we provide people with a context that's going to disambiguate between the high versus low scope interpretation. then we just ask people whether a given target sentence is true or false under that context. Okay? So here's a context. At a recent archaeology conference, Emily said that her research team found evidence to prove that a famous ancient city was actually built by aliens. But she didn't release the name of the city. So that last sentence I highlighted in red is the critical information for this context. And that was the Chinese there for people who want to read. So given that context, we asked people to judge the truth value of this target. So Emily announced her team discovered aliens built which city. So this is English gloss presented in the Chinese word order. Okay? So let's see what truth value judgment people should give under which scope interpretation. Suppose a participant read that sentence and interpreted it as having a low scope reading. So the low scope reading gets translated in English as something like, Emily announced her team discovered which city was built by aliens. Okay? If you're not a native English speaker, you have to be a semanticist to understand what that means. So the truth value of that roughly gets translated into Emily announced her team discovered the answer to this question, which city was built by aliens, all right? So given that truth condition, the low scope reading would be true in that context because Emily did make the announcement that her team made such a discovery, all right? On the other hand, if the participant obtained a high scope reading that gets translated into Emily announced which city her team discovered was built by aliens, the truth condition roughly is Emily announced the answer to this question, which city did her team discover was built by aliens, which is false in that context because she didn't release the identity of the city, okay? So based on that reasoning, if people give us answer true, then we know they get a low scope interpretation. If they give us back false, we know they obtained a high scope reading, all right? So under the exact same context, we also have a different condition where we change the matrix verb from something like announce to its antonym, like a negative verb, hide. We did this in order to balance out the true-false answers people would give us. Because under this matrix verb, the true and false judgment actually would flip. So now if people get a low scope reading, that would mean Emily hit the fact that her team discovered which city was built by aliens, then they should give false as their judgment. On the other hand, if they obtain a high scope reading, that will be Emily hit which city her team discovered was built by aliens, which is actually true given that context. So these two different matrix verbs is going to give you exactly opposite judgments. Okay? So now come to the results. So here is the averaged responses. We're not plotting the yes or no, true or false answers. We're plotting actually the inferred scope interpretation we inferred from their responses. So you can see that by average, people prefer the high scope interpretation much more than they choose the low scope interpretation, okay? And you can split it by the matrix verbs we used, and it's the same for both kinds of verbs. Either it's the positive verb or its negative counterpart, okay? So here is the puzzle then. Ambiguity based on the truth value judgment seems to be resolved towards a more complex parse. So in our previous data, in the first two experiments, we showed you that high scope readings are preferred in the third experiment, high scope readings are preferred for ambiguous sentences despite their enhanced parsing complexity, which we showed in the first two experiments. So now we were trying to get a handle on why people prefer this high scope reading, which seems to be a harder or longer dependency to construct. We can start by thinking what a rational listener may do. So the base rule would predict the following. So the probability of somebody interpret this ambiguous sentence to give a high scope reading should equal to this term on the right, which is related to both the production bias, so the likelihood of them using that ambiguous form given the high reading, and the other term is the prior expectations. So the left side of this equation we already estimated, we have the empirical estimate from the truth value judgment. We also did studies to estimate the two empirical terms on the right. And it turns out this actually doesn't completely predict the truth value judgment. So what turns out to be more relevant or a better predictor is actually this. So we can predict the choose value judgment, so the proportion of them obtaining a high scope rating, if we just look at their production bias, removing the prior part. So, so on the left hand, that value is estimated by the choose value judgment. So in the rest of the talk, I'm going to tell you how we estimated the right side, giving production task. So in this production task, the procedure is actually simple. We provided a context that biased people towards a particular scope interpretation. Then we give them some fragments. We say, can you just put these fragments together to form a sentence? You can add other stuff you want, but you have to use these fragments, and then as long as the sentence is compatible with this context. Okay? So what we measured is we calculated the proportion of the ambiguous W-C true sentence forms, just like the ones we give them in the choose value judgment task. So here's an example. So here's an example where we give them a context that bias them towards a high scope interpretation, and then we give them this verb announce. Okay? So the context is the same archaeology conference context, and the critical information is there at the end that says she also released name of the city. So in this case, the high scope interpretation should be true, and we give them these 4 fragments. Emily announced which city, built, her team discovered, and these fragments are scrambled so people don't get cues for word order. And we also did similar things to provide low scope compatible context and so on. So because depending on the matrix verb is announce or a negative counterpart, hide, there are different choose conditions, so we estimated the production bias separately for those 2 kinds of verbs. Okay, so we created different context for a verb like hide. Sorry, I didn't have time to show the actual context because my time is up. So just take a look at the averaged production bias. So on the x-axis, we plot verbs like the matrix verb is either announce or hide. On the y-axis is the proportion of people giving back a sentence form that has this ambiguous WH in it. Or, sorry, that's the word order that would give rise to ambiguity. Okay? So you can already see that when the matrix verb is announced, if the context is such that bias people towards a high scope interpretation, people are more likely to go back this ambiguous WH&C true construction. But if the context bias towards a low reading, then people are less likely to do so. And this pattern somehow flipped when the matrix verb is hide. Okay? So it's an interesting question in itself as to why we find production bias of this kind. And we have some thoughts on that, and if you want to talk about that, I'm happy to share my thoughts. But for now, we just want to go back to our original question, can we find a correlation between their production bias and their choose value judgments? So again, just to remind you, the left side is estimated by the choose value judgment, and the right side is estimated by the production task. And in the plot I'm going to show you next, the x-axis plot the estimate from the production task, and the y-axis plots the estimate from the choose value judgment. Okay? So here is the correlation when you take items that have the matrix verb announce. You do see this significant correlation between their production bias and their choose value judgments. However, what's interesting is if you look at those items that have matrix verb hide, which is the negative counterpart of announce, you don't see such correlation. Okay? So this is surprising to us, so we had a thought about why this may be the case, and here is just a post-hoc thought, so take it with a grain of salt. That is, the negative counterpart, when you think about how negation is comprehended, there was a talk about negation actually yesterday, you can think about it needs to be decomposed, at least in the representation. We're not making any timing commitment here. So in the representation, it seems to be a negation is comprehended in terms of a negative operator plus a positive proposition. So if you think it in that way, you may wonder whether the correct correlation should be between, so the comprehension on items that have hide as their matrix verb should be correlated with the production bias that estimated from verbs like announce rather than verbs like hide themselves. And it actually turned out to be the case. So if you just take the production data we have, those estimated for the announced verbs, they actually predict the comprehension bias for items with height as the matrix verb. Okay? So just to summarize, in the last two experiments, we showed that scope interpretation bias is better explained by production bias. Again, there's a question here why production bias is the way they are, instead of parsing difficulty. And there was this surprising result at the end. What happened? I know I need to stop, but all right. There's this other finding at the end that, sorry. All right, I don't know where I should go. Sorry about that. Yes. So there's this little surprising finding about negative predicates, so we need more work to understand how negation is comprehended. Okay, so conclusion and future work. The two empirical findings I want to establish, one is about COVID dependency. We do have evidence to show that people are sensitive to silent dependencies and that the formation process of that dependency is subject to similar constraints as overt dependencies, such as locality bias. But at the same time, we find this contrast between the parsing data and the interpretation data. So the ultimate scope interpretation seems to not be entirely determined by parsing difficulty. And finally, that raises questions for future work. So the first thing is about what kind of processing model that can accommodate certain degree of dissociation between incremental structure parsing and global interpretation. And second is more work needs to be done in order to understand the interaction between production and comprehension. That's not a new problem. A lot of previous literature have discussed this. A lot of discussion at this conference is about the interaction between production and comprehension. But I actually think the current case is slightly more challenging than the usual cases people have talked about. And I'm happy to share some thoughts in the question period. And thank you, and thank our funding agency.
I see why you kept tripping. Jeff Runner, University of Rochester. This was really interesting. I had a couple things. The first, I'm just going to say the first thing, and that is the original judgments on the believe sentences make it look like it actually isn't ambiguous. I mean, isn't unambiguous in the sense that it looks like people don't actually like the long distance interpretation. So I'm just wondering, so you characterize the believe cases being unambiguous and the other cases being ambiguous, but it actually looks like you're comparing a grammatical interpretation to an ungrammatical one. Do you just have a comment about that?
No, the believe case is actually grammatical. I think it's not.
Point 4 was the.
So they actually can get, so there's this issue about what acceptability judgment is measuring, and then what the choose value judgment pass is measuring. So there are two things. So if you just look at the acceptability judgment, that's the gray bar here, it's very low, it's true. But it's actually, we do have actual ungrammatical fillers in the sentence, and these are better than those ones. And at the same time, there's also, there are two conditions in the choose value judgment I didn't present here. Those conditions maintain the matrix verb to be either announce or hide, but we changed the local verb to a believe kind of verb. So those are unambiguous in those, under the same context we provided. And people can actually get the interpretation correctly given the choose value judgment. They don't make mistakes in the judgment there. So those made us believe they actually do know what the sentence means. So I think this raises the question about what acceptability, what's the mechanism that give you this acceptability judgment, why the acceptability judgment is so low, yeah.
Yeah. Josh Hartshorn, Boston College. I actually had a question about the one in the long abstract, which is how you measured the prior probabilities of the of the messages in your, for your model, it looked like from the long abstract, what you did was measure the prior comprehension probabilities. So,
Right.
And that I found surprising because I would be used to seeing this sort of model. You'd say the posterior probability that a particular message was intended given a production would be proportional to the probability of that production given that the message was intended times the prior probability of the message. So how likely was it the person who would want to have communicated this particular idea, in this case the high scope version or the low scope version? But it looks like that's not what you measured?
Yeah, no, I would love to know more about whether whether our way of measuring prior is not accurate. That's drive this finding here. But the prior we currently measured is basically saying here. So we basically provided people a neutral context and say, given, for example, given the context that there was an archaeology conference, Emily did a report. Given that very neutral context, we just asked people, okay, now in that context, how likely do you think the following things happened? For example, the following thing is she made a report about her discovery, but she didn't release the name of the city.
Oh.
And another condition would be, okay, how likely is this situation happen in which she did make a report and she also told people the name of the city. So those are the two interpretations that's relevant for our purpose. We measured how each of interpretation, how likely those situation is going to arise for people. So,
Right. Thank you for the clarification.
Yeah.
Brian, your microphone takes scope over this one.
Oh.
Hi, so fabulous talk. I liked it. Brian Dillon, UMass Amherst. I was really interested in the puzzle you described where you're seeing this difference between the online parsing and the offline interpretation. And I guess I just wanted to ask your current thoughts or let you speculate a bit on what you think the processing model might look like that would allow for that difference between the online parsing and the offline interpretation preferences.
Right. I'm actually not particularly sure I'm going to characterize this as an online versus offline thing. I don't have the online data. You can imagine you put people in the choose value judgment task and still measure some online data, right? I don't have that data. I think what current thought is really what, because the parsing difficulty is, the conclusions about parsing difficulty is made based on acceptability judgment, and given that task, their reading time. So I think it's really about what decision process goes into making the acceptability judgment. So one thought could be that if you imagine this related back to your talk, so one possibility is that you have these two possible parsers, and somehow in our case, the local one is much easier to be accessed, and then once you find there is such a parse, you're going to say, yes, it's acceptable. You don't really care if there's another one that's acceptable. But once you fail to find that parse, maybe there's an internal threshold. You just need to make your acceptability judgment, and then past that threshold, you're just going to say, no, this is not acceptable, right? So if that's sort of the mechanism that gives you the judgment, then I feel like it doesn't directly speak to the issue about offline versus online comprehension, yeah.
Great, thank you.
Thanks. I'm sorry, that's all the time we have, so let's thank Ming again. Our next talk will be delivered by Matthew Jones and is entitled Language Change Explains the Presence of Iconicity in the Vocabulary.
Okay, so I'm going to be talking about iconicity and cultural evolution. What is iconicity? We've heard a little bit about it this week already, but it's resemblance between form and meaning in a sign, and that sign in the broad sense, it can be a word, it can be a gesture. The terminology goes back to Charles Sanders Peirce there, Cambridge, Massachusetts native, and in spite of famous dictums about the arbitrariness of language. There's actually quite a lot of it in natural language. In languages like English, we have onomatopoeia, words like splash, bang, meow. We've also got iconicity and gesture. But then there are other spoken languages, like famously Japanese, but there are lots of others that have sound symbolic classes of words that are iconic for things like manner of motion and sensation. And then, of course, there's lots and lots of iconicity in the signed languages of the world. There are a couple of examples from British Sign Language there. Now, people who work on this are of the opinion that this is not just ornamental. For both signed and spoken languages, there are, in at least certain contexts, advantages to iconicity in word learning, in processing. It's the case that a disproportionate number of early acquired words and signs are iconic. And iconicity researchers usually advert to this kind of thing when they're trying to explain the presence of iconicity in the vocabulary. But that's not really a complete explanation, because it's not like God sat down and decided, I'm going to design the vocabularies of language to make things easier for the people who are using them. So we need some kind of mechanism that introduces this iconicity and optimizes things. So what I'm going to suggest is that this mechanism is the kind of cultural evolutionary process we've already heard about at this conference from people like Morton and Simon and Masha. The basic idea is that possibilities in the language space that reflect biases in production or in learnability ought to be favored by broadly Darwinian cultural evolutionary processes. Now, this argument has been applied to various aspects of the grammar, but as I say, I'm going to turn it to vocabulary. So how am I going to assess the plausibility of this claim? Well, I'm going to use the iterated learning method that, again, we've heard about already, so I won't labor this too much, but just to recap, how it works is it's like the game that's called Chinese Whispers in the UK, Telephone in the US. Essentially, you teach something to a first person, and then you test them, you teach what comes out of that to a second person, test them and teach it to a third person or generation, in each case retaining the mistakes that each person makes. And what, of course, you find is that what you put in initially evolves over these generations, and it evolves in many cases in interesting and non-arbitrary ways that maximize the learnability of the language you're teaching. So what I'm going to ask is, will iconicity emerge from an initially arbitrary language in suitable iterated learning experiments? So here are the kinds of iconicity I'm going to be looking for. First one I'm going to call sound shape iconicity. This is the stuff of the Kiki-Buber effect. The basic observation is that you have these two shapes, one's sharp, one's rounded. You say to people, one of these is called Buber, one is called Kiki, which is which? In general, a majority of people are going to say Kiki is spiky, Buber is rounded. This is relatively robust cross-culturally, cross-linguistically, so that's the first kind of iconicity. The second kind of iconicity is what I'm going to call motion iconicity. It's basically a correlation between word length and the duration of the event that's being described. So this is something you see in various sound symbolic languages. Sometimes vowels are elongated for more durative events. Sometimes, as in this example from Japanese, you reduplicate syllables in order to signify repetition. So bearing those kinds of iconicity in mind, I'm going to show you the stimuli that the participants in these experiments were learning names for. Now, they were actually videos, so bear that in mind. In each case, the video was about 5 seconds long. You have a shape at the bottom of the screen. Half the shapes were rounded, half the shapes were spiky. As you can see, color just serves to generate enough of them to make the task challenging. And then the arrows here represent motion. The shapes without arrows didn't move at all. They just sat there at the bottom of the screen. With one arrow, you had a single upward stroke, and with an up and down arrow, they bounced up and down repeatedly. So the basic idea is that these stimuli are differentiated, one on shape, two on duration of motion, which are the things we're looking for iconicity to target. So here's how it worked. There were two experiments. They were essentially exactly the same, except that the first one used text-based names. The second one used speech-based names. In each case, a participant would sit at a computer screen. They'd learn the names for these stimuli just by seeing one of these videos and then either hearing or seeing the name for that item, depending on the experiment. And then at the end of the session, they would be tested by, again, seeing each of these videos, but then having to produce the name, either by typing it in or speaking it into a microphone in each case. So in each experiment, there were 6 chains, 6 of these telephone chains, each of 10 generations of Anglophone, adult Anglophone participants. We started off with an arbitrary initial language, so a language that didn't incorporate either of these kinds of iconicity and wasn't compositional either. And our prediction is that iconicity will emerge for shape and motion. So first of all, I'm going to show you some data speaking to learnability. So this is just for the first text-based experiment because we could readily assess the error rate there because our words were already in sort of letters that we could do an edit distance metric on. But what we found is that error rate decreased over the course of the experiment. So we've got generation on the x-axis there, error rate on the y-axis. This, to preempt what I'm about to show you, probably at least partly reflects the emergence of iconicity, but it's something you'd expect in this kind of paradigm for very general reasons. As I say, Darwinian processes tend to make the language more learnable. So moving now to sound shape iconicity, 2 graphs, it's text on the left, speech on the right. Again, generation is on the x-axis. On the y-axis, we have norm-based metrics of the roundness and spikiness of the names that participants produced. We just had people online norm those. And what we see is that even though they start in roughly the same place, over the generations, the names for rounded and spiky stimuli diverge in the expected direction. So to caricature slightly, spiky stimuli end up with names like Zediki, whereas rounded stimuli end up with names like Subo. So moving now to motion, duration of motion iconicity. Again, we see a similar thing. So text on the left, speech on the right, generation on the x-axis. This time length on the y-axis. That's measured in letters for the text experiment, syllables for the speech experiment. And again, we see the different classes of stimuli, so the still ones, the ones that move up in a single stroke, and the ones that bounce up and down, diverging in the expected direction. So the bouncing stimuli get longer names. On average, the still stimuli tend to get shorter names. So, conclusions. So this is what I tentatively conclude from this. So we saw iconicity emerge in a model of cultural evolution of language from an initially arbitrary language. So it seems like, in principle at least, this kind of dynamic is sufficient to explain the presence of iconicity in the vocabulary. Now, there's then a further question about what the nature of the biases that drive that are. Some people think they might be language specific. I suspect that is, I don't think what I've shown you refutes that, but I think that hypothesis may be redundant, and you can ask me about that if you're interested. But what that means for iconicity is if you do buy the story that at least some language universals or design features are a result of domain general biases plus this kind of cultural evolutionary process, well then iconicity is on the same footing as those other universals or design features. I think this interestingly recontextualizes the fact that you tend to see iconicity being lost from new sign languages. Sometimes that is described as if it's a terminal decline in iconicity. I think this suggests it might be convergence towards an equilibrium, non-zero equilibrium. If you start off with too much, you lose some, but if you start off with not enough, you gain some. And then finally, some people have suggested that in language evolution, biologically, not culturally, you start off with an iconic proto-language. I'm not taking a position on that, but a lot of people who do assume that have said, well, that proto-language must have been gestural because we can't get enough iconicity into words. I think this suggests that might not be true. We have two kinds of iconicity for events and for objects, respectively. So I will skip that. Thanks very much, my collaborators, of course. Thank you to Simon Kirby and Liz Wanacott for valuable comments. Also the CUNY reviewers, and thank you for listening.
3 minutes for questions.
Hi, I'm Annie Sanghaas from Barnard College. I have two short questions, I think, but they kind of are probing at what level you think these mechanisms are operating. So do you think you would have gotten the same result if children had done this task and or non-Anglophones? And another is, how do you reconcile this with the fact that sign languages actually decrease in iconicity over time, not increase, and the respective roles that children and adults play in language emergence?
Okay, so first thing, would it happen with children? I'd love to do this with children at some point, though it's difficult to do this kind of stuff with children. I predict it would happen, partly because we know that the biases, the kinds of iconicity we are dealing with here also pertain in children. There's work on this sounds to shape iconicity stuff with children. Non-Anglophones, again, I would predict that if anything, English would be a language that doesn't predispose you to introducing iconicity, because it's a language that's relatively poor in iconicity. If we did this with, say, Japanese people, I'd predict more iconicity. The second question, the sign languages losing iconicity, as I say, I don't think that's a terminal decline, right? There are sign languages that are really pretty old. British Sign Language seems to be hundreds of years old. Still got lots of iconicity. So I think if you start off with home sign feeding the development of a sign language, there'll be more iconicity there than is useful in a mature language, and you will lose some, but you won't lose it all. Some of it is still adaptive.
Right. So the key piece there, though, is if you're talking about home sign, now you're talking about cases that don't have any iterations of learners, right? But yet you're guessing that it would be high in iconicity at its initiation, right? So doesn't that kind of go against the story you've told here? Because if you're basically saying your seed is going to start out, your seed that comes from a human creator is going to start out at its peak of iconicity.
Yeah, what I'm claiming here is that there is a pressure to maintain iconicity, right? The claim is not that languages grow in iconicity all the time. It's that for principled reasons to do with the interaction of human biases and cultural evolution, you would expect to retain some amount of iconicity, even if it's not something that's absolutely necessary for bootstrapping communication like it is in home
Right.
sign. Does that make sense?
Yeah, but I'm actually pointing out the reverse. Like, where does it come from in the seed of home sign? Which maybe is
Where does the iconicity come from? So, I mean, Susan would know more about this than me, but I assume it's a kind of thing. If you're a kid and you don't share a language with anyone you're around, you improvise that to try and come up with signs that are spontaneously comprehensible. And I'm perfectly happy with that being one of the mechanisms.
So then you don't need the account for increasing over iterations, right? You've already got it in your story.
But I'm not necessarily, so I want to explain why even in really old languages like, English or whatever, you would still expect to see a certain amount of iconicity. If it's going to be kept, there needs to be a pressure that stays there even after.
That's a
Oh, wait, just let me say one thing, okay. So I think that, along the same lines here, I think control condition might be really important. That is to have the same person keep going over time. Because although it's very clear that this cultural transmission can maintain iconicity, it's not clear that it's necessary, which I think is the point, part of the point that Annie's making. And a control condition would at least help to shine light on this question, because I suspect that you would have the same sort of change, or you might find the same change in iconicity with a control condition.
Okay,
So,
yeah,
okay.
very interesting. Thank you.
Okay, our next talk will be delivered by Limor Raviv and is entitled Compositional Structure Can Emerge Without Generational Transmission. Okay. Can you hear me? Great. So welcome to today's talk. This is joint work with Shiri Leverie and Antje Meer at the Max Planck Institute. And just to set the framework, thank you very much for starting with this. What we talk about when we're talking about the emergence of linguistic structure, at least for the purpose of this talk, is I'm going to focus only on the transition from a state of some sort of a holistic proto-language to a state of a full-blown language that looks something like the languages we speak today, with systematic structure and grammar. And one of the hallmarks of this transition is claimed to be the emergence of compositional structure. So basically the emergence of some sort of ability to reuse elements in a systematic way to get different types of meanings. And in a recent study in the field, Simon Kirby and colleagues have argued that this compositionality emerges as a trade-off between two forces, expressibility on one side and compressibility on the other hand. And the way this works is the following. So they argue that on one hand, you have a pressure for languages to be expressive. This pressure pushes languages to be this maximally informative system. And they argue that it's naturally imposed during communication. So because the goal of communication is to get your message across, to be understood, then the expressivity pressure will emerge during communication. But on the other hand, languages also are pressured to be compressed. So there is another pressure on languages, basically to have some sort of a minimalistic, transparent system with very clear and productive rules that can generalize to an infinite set of meanings. And they argue that this pressure is imposed during transmission to new learners. So because the language is being learned again and again and again, it's pressured to be compressible and learnable and transparent. So when these two forces come together, what we have is basically on one hand a language that needs to be minimalistic and easy, and on the other hand a language that needs to be expressive and full. So basically the solution for this is to develop compositional structure. And the way they do this, as we just seen in laboratory settings, is basically to take the diffusion chain paradigm, introduce communication to it. So we have a dyadic diffusion chain in which a pair of participants come to the lab, they're trained on an artificial language, and after several communication rounds, their language is the input for the next pair. And when you do this for several rounds, what you find is that indeed compositionality emerges. So what I'd like to show you here is that, So there is systematic reuse of elements. So for example, this shape is always marked with ege, and you also have marking for the texture. So for example, wawa for the checkerboard, woo-woo for the dotted ones. So this is a very compositional language. And what I'd like to talk about today in this current study is just to expand on this current framework by focusing on this bit. So what I'd like to argue is that, in fact, pressure for compressibility does not necessarily need to arise during transmission to new learners. I would like to say that there are other sources for compressibility pressure rather than generation turnover. In fact, what I'd like to argue is that compressibility can be during communication. So I'm going to try to convince you today that compositional structure can really emerge only in communication alone, as long as the communication includes two features. And these are two real properties of language use, which you find in natural settings and natural environments. So the first thing is if the communication includes talking to multiple people. So when you interact to a lot of people, this holistic supermaximal compositional system, non-compositional system, is kind of hard because you need to converge with a lot of people on it. You have a lot of input variability from all the people you talk with. And we know that when there's a lot of input variability, there's more pressure to overcome it. There's more noise. And indeed, input variability is one of the things that highlights and boosts systematicity. In fact, there are some researchers like Ray and Grice that argue that talking to strangers is one of the driving forces pushing languages to be predictable and structured. So this is one possible source for compressibility pressure that can emerge during communication. The other thing is having some sort of an expanding meaning space. So in the real world, we don't just talk about a closed set of meanings like often done in this artificial language experiments, but really we have more and more things to talk about, sometimes an infinite set, pushing languages to again have some sort of a productive rule that I can use to talk about new and more meanings as they enter the language. Okay, so indeed these two pressures are possible sources for compressibility within communication. So our design, I'm going to show you that we had basically different micro-societies. They were sitting together. We had 3 groups of 4 people. They were sitting together and they were playing a communication game. They were doing this in alternating dyads for different rounds. So what this means is that for the first round, for example, participant A and B were playing together, and C and D were playing together. They were having several games, in this case 23. And after 23 games, they switched. For example, participant A is now playing with D, and B is now playing with C. And then for the next round, they switch again, and we do this for 6 rounds. They were interacting about different novel items that I'll show you in a minute. And importantly, they were doing this using only an artificial language that they come up with together in the first round of the game. So the basic design looked something like this. It's a low-tech pen and paper experiment. So one participant, they were sitting, this is a dyad interaction. There's a barrier between the two. One participant sees an item, and he needs to describe it in this artificial language, or fantasy language, as we called it. And then he shows this word to the other participant. The other participant is faced with a grid, and that has 8 different items, and they can make a selection what they think participant A meant. They can make the right selection and get a point, and the whole point of the game is to get as many points as possible, and we encourage the participants also with an extra prize. But you can also choose the wrong item. But importantly, no matter what you choose, participants get feedback. So participant A knows what participant B selected, and participant B knows what participant A meant. Okay, so they get a chance to improve as the game progresses. So our materials, we had basically a meaning space that had 4 different shapes, and they appeared in different types, in different sizes. So it was a continuous meaning space, not a categorical meaning space. And also each item had a different idiosyncratic feature, texture. So that is, if participants really want to come up with this maximally informative system, they can. Okay? It makes sense. And as I explained, this experiment is going to have 2 important features of real communication. One of them is going to be talking to switching partners. So each round, participants switch who they're talking with. And again, the meaning space is expanding. So what this means is that we start out with having just 8 items in the first round, and we add more and more items as the game progresses until ending with 23 items in the last round. Okay, so what did we find? We didn't only look at structure, we looked at various different measures to categorize the system. So I'm going to start by showing you the convergence. I'm going to start by showing you how participants develop a shared lexicon together. So what we're doing, we're measuring the distances between the words produced by different participants for the same item. So how much are they similar to one another? And what we find is that there is, when we put this in a mixed effect model, that there is a significant effect of item's age. So what you see is that as older the item gets in the game, participants agree the distances between the different labels of participants is reduced. So participants agree on what is the word for that item if it's old in the game. But also we see this interesting interaction with round. So in later rounds, participants actually need less time to converge on a new item. So when a new item enters the language in a late round, participants kind of already agree on what to call it, and this is faster in later rounds. This is supposedly because participants have developed some sort of a predictable, perhaps compositional system that kind of allows them to agree on what the word should look like for a new item even before it enters the language. We also looked at stability. So this is often called learnability in Kirby studies. This is basically the differences, the change in the language over time. It's not an error because there's not a real answer here. There's not a true or false. So we looked at the stability again by looking at the differences in labels across time. And what we see is that there is a marginal effect for items age. This is perhaps a power issue because there are just 3 groups. Every line here is a different group. And then what we see is that older items are basically more stable. They change less as they are older in the game. And again, we find this nice marginal interaction with round, so it matters less and less how old the items are as the games progress. Participants have supposedly developed this system that allows them to agree on what the word should look like. Okay, so looking at structure, we measure this by looking at the correlations between meanings and string distances. This gives us an estimate of whether similar meanings are being expressed using similar strings. This is the standard way to look at compositionality here. And what we see is that indeed there is a significant increase in structure over time. And this is true when looking at raw correlations and also when looking at z-scores produced by the Mantel test, which is often the measure given for compositionality in these experiments. And I'd like to give you an example of one such language. So this is a language produced by one participant in the last generation. What you can see is that there is a unique string. The coloring here is just for visualization purposes, had nothing to do with the analysis. It's just to make my life easier and hopefully yours. So what you can see is that there is a unique string that is associated with each of the shapes. And there's also some morphology emerging for size. So it seems like, for example, big items of shape 4 get an additional prefix za, and medium items of shape 4 and 2 get zo. There's also a beginning of perhaps an iconic suffix for something small, ni. But just to set your mind that this is not only based on just three groups. So ever since we submitted the abstract, we already run a new version of this experiment, which is a computerized version. Basically, we changed size into motion. So we had different items, and they were just moving on the screen in different directions instead of being in different sizes. So it also gives this more of an event-like feeling. And indeed, again, with 3 more groups, what we find is that there is a significant increase in structure over time, even to a point of 0.6 correlation, which is quite amazing. And I want to show you an example of how this looks like. Don't be alarmed. Basically, what you can see in this graph, so the different, okay. So the different rays indicate the direction to which the item was going to. And the different box color is a different type of shape. So if you can see, shape 4, no matter where it goes, always gets tawe. Shape 3, no matter where it goes, always gets spunk. And there is also a nice morphology for direction. So what we can see is that everything that's in the top goes up, gets a ho. Everything that goes down gets an u. And there is also some morphology for right and left, which is really interesting. Okay, so indeed we found that compositionality can emerge without generational turnover. And just to conclude, I argued that compressibility pressures can indeed arise from various sources, not just transmission and learning. In fact, I showed you that it can emerge during communication alone, as long as it includes these 2 important features about language use. And the implications here. So for one, this study suggests that compositionality can actually emerge in a communication in a single generation. It may take time to stabilize, and it may take time to expand to other dimensions, but the essence or the seed of compositionality can already be there within a generation. This is relevant for developing sign languages and for creoles, which often have this discussion whether you need a new generation for several things. So at least for the seed of compositional structure, our study suggests that you don't. Okay. And then finally, there is another implication here, and that is perhaps everyday properties of the way people interact and language use can really impose different types of compressibility pressures. So imagine, for example, that cross-cultural differences in interaction patterns or input variability patterns, how many people you interact with, for example, can really bring about different types of pressures and maybe affect linguistic structure. So the reason we've developed this whole paradigm is because we wanted to be able to compare different types of groups. So now in the lab, we're going to look at big groups versus small groups, tightly connected groups versus sparse groups, and so on. So that's it. I'd like to thank everyone who helped programming, helped with coding, gave advice, and so on, and thank you.
2 minutes. Thank you. This was very interesting. I'm wondering, so you've hypothesized there's these 2 factors that need to be present. Did you manipulate them independently?
So this was done by the original Simon Kirby study in 2015 to basically want to say that if you only have expressivity pressures, then you get a very holistic, super expressive language, but very holistic and hard to learn. On the other hand, if you only have learning, then you get sometimes these very learnable and compressed language.
Sorry,
but
I was unclear. I mean, talking to multiple people and emergence of new meanings.
No, we did these two combined. Basically, the point of developing this paradigm was we really wanted to have a design that we can have groups together and look at differences in compositionality without having many people come to the lab, because it's very hard to do with a group of, for example, 8 people. So basically, we wanted to give the optimal conditions for compositionality to emerge, so we didn't.
I just wonder if multiple people would suffice, because I'm not, I mean, although meanings expand over development, I don't get a sense that there's that much that, like, once you reach some adult state, I feel like we talk about the same things all the time, as evidenced by very similar themes in literature, like over, many generations.
Well,
So I'm not sure if that's a
Well, this is a miniature language, right? So like,
sure.
Yeah, so having only 8 items and not increasing it might not be enough, I think. Yep.
Hi, Christopher Hammerly, Department of Linguistics at UMass Amherst. I want to ask a question about your definition of compositionality. It seems more like what you're referring to as compositionality is more like conjunction rather than what we normally think of as compositionality in semantics, which would be something like saturation of an argument of a function, say verb like runs, where you would saturate the argument of that with John, so John runs. Whereas in this experiment, it seems more like you're getting something like an object is green and an object is big, which isn't the same sort of compositionality in the Fregean sense of the term.
Well, I'm not sure I follow, because so to me, and also in the literature that this cultural evolution literature, the idea is that compositionality is basically the ability to reuse elements. And to do this when you say John and walked, I don't see how that's very
That's not John and walked, it's
sorry.
John, yeah.
Sorry.
Yeah. So it's a broader issue with the use of compositionality in the literature, not just within.
Okay, well, I follow this definition of compositionality. So basically, the ability, the difference, it's contrasted with a holistic system.
Right. So I guess what my question would be is, do you have evidence of compositionality, not in the conjunctive sense of like X is green and X is big, but in the sense of...
Yeah, I'm not a semanticist, so I'm not sure I understand this, the subtle difference that you're trying to make. I'm sorry. We can talk about this later, though.
All right,
I'd love
thank
to.
you.
Unfortunately, we're going to have to take it offline again, sorry. We have to move on to our last talk. Thank you, Limor.
Let's see if this actually works. Oh, not this one. This one.
Okay, so our last talk of the session is entitled Redundancy and the Lexicon, the Effect of Word Informativity on Word Shape, delivered by Adam King.
All right. Give me a second. Okay, thank you very much for coming. I'm Adam King, and today I'll be talking about information in word shape. This is incorporating a little new data and analyses that I've done since submitting the abstract, so hence redundancy is gone because it was redundant. Already starting off good. So this is work that I've been doing with Andy Wadel over at the SUNY University of Arizona. And I'd like to start with a quote that I think is sort of underused in the literature relating to information and the lexicon and word size. And that is, it takes a long time to say anything in Old Entish, and we never say anything unless it's worth taking a long time to say. And what exactly what this means, that was a quote from Lord of the Rings for those who weren't culturally versed in that sort of thing, is that we know that word length is correlated with how informative a word is. And in this case, I'm talking about sort of surprisal or contextual probability. And our hypothesis or question is the distribution of information within the words also related to the informativity of the word itself? So basically, we know this already, that if you look at sort of word length, we see that more informative words tend to be bigger or longer, more phonemes or more phones in them, whereas less informative words tend to be shorter, fewer phonemes. Our question or prediction is that we might see something like this, where we still see the same sort of length distinction, but rather we see that there is more informative material at the beginning, less informative material at the end of all words, and this sort of pattern is even greater for more surprising or more informative words. So now I want to kind of talk about why we might even expect this shape at all, this sort of triangular shape. And that is sort of incremental processing. So there's a lot of work on incremental processing in the literature on spoken word recognition, and though there is sort of a little debate in exactly how it works, we know that listeners process words incrementally. That is, they don't have to wait till the very end of hearing a word, suddenly know that they've heard a word boundary, and then go look it up. They're able to incorporate information as they're getting it into making their identification of the word, and also competitively. So when you have very little information, a lot of different words are activated, and as you get more and more and more information, you're gradually able to sort of reduce the set of possible words down to a singular small set. So I want to stay on this slide for a little bit because it kind of goes over how exactly I'm calculating the informativity of a given segment. So I'm using the formula in the top right to calculate how informative a segment is. That's pretty much the probability of the segment given the previous segments divided by the probability of the previous segments in the word compared across the rest of the lexicon, and then taking the negative log probability of that, the negative log of that greater probability. And another sort of less mathy, more abstract way to think of this is basically the amount of information a segment gives you is related to how much it shrinks the competition. So if it shrinks the competition a lot, it's really helping the listener make identification. And kind of further from that, we would expect later we get in the word, the segments are just going to be gradually less and less informative because the set of possible words are going to be smaller and smaller because we've already gotten all this information loaded at the beginning. So on the left, I have a chart where I'm going to be charting out the actual segmental information for 2 words in English. The x-axis is the segment position, so where it is in the word, and the y-axis is an actual, in bits, how much information each segment has. So starting with the word monster, you see that the first sound has about 5 bits of information, but then once we get to the ah, we have much less information because we've already reduced the set of competition from that first ah, ma. And as we go through the word, we see we get less and less until about we get to this S where we're about at 0. Under ideal conditions, assuming that the listener has heard everything, there's no other word in the lexicon that starts with this prefix or this set of sequences, this sequence of sounds. So word identification should have happened. And then we get 2 extra sounds. Then we have another word, thorax, which is starting with much more information. So this theta, this th sound is rarer at the beginning of words, so it's more surprising, and this gives you more information about the word you're hearing, and then you get this beautiful open O, which I can't do. And then as you go down, you get to less and less information, and just for clarity's sake, the final sounds do hit sort of this 0 line, but just so they're not collapsing on each other, they're above a bit. But anyway, if you chart this, you see we get this sort of gradual curve where we start with more information and gradually get to the end. And also, not all words are equal. Some words will start with more information, some words will start with less informative material, but you see that they all sort of collapse or kind of converge around the later segments, segment 5 in this case, because by that time you'd expect the listener to have already figured out the word. So now rationale in more detail. We know that listeners are able to use different types of information to make predictions about the words they're hearing. They're able to use sort of cues from the segments themselves within the word, and also context, the words around that, to help them make identifications. We also know that earlier segments just tend to be more informative than later segments because they're able to sort of restrict the competition more. And now, in other literature, we know that speakers tend to enhance or hyperarticulate more informative segments and sort of reduce less informative segments. And we know that repeated online contextual enhancement and reduction can shift long-term lexical representation. So this is essentially if a word or a segment happens to be contextually predictable a lot, even in cases where it's not predictable, it will also undergo reduction. Or if a word happens to be in a context a lot where it's very surprising, it'll undergo enhancement more often than not. So, taking all of these into consideration, our hypothesis with this big flashy thing is that we predict that over time the lexicon evolves in a way so that less predictable words are more predictable by early sounds. So they start with more predictable or less predictable, more surprising sounds. Another way of thinking of this is we expect that over time, as certain segments are enhanced a lot, they'll stay in the lexicon. As certain segments are reduced a lot, they'll disappear or reduce in the lexicon, and the most informative segments happen to be the ones that would be at the beginning of a surprising word because you're not expecting that word, and that word needs a little extra boost from this word itself. Yeah, so this is sort of what we expect, that we're going to see words that are more informative or more surprising to start with. More material at the beginning, more informative material at the beginning, and less informative words to start with, less informative material. So before I get into that, I want to go into the methods and materials, how I was able to calculate all this. I used corpus, in this case the COCA corpus, the spoken corpus, because I expected that this is something that would be online for spoken language, and I wanted to get word frequencies that are based on spoken language rather than much bigger corpora like the Google Ngrams, which are much bigger than this. And I calculated word surprisal using the negative log unigram probability. So I have also tried models where I've used sort of bigger n-grams like that, and I'd be very happy to talk about in the questions. But for right now, this model just uses the negative log unigram probability. I used the phonetic transcriptions from the Carnegie Mellon Pronouncing Dictionary, which is about 27,000 words. And this is so I could take the giant cluster something that English spelling is and actually reduce it down to the actual segments, the actual like phonological sounds that we'd expect. And finally, I used the Selleck's corpus to make sure that I was selecting only monomorphemes, because I expect that derivation morphology, compounding, and all sorts of other crazy stuff might sort of affect how informative a segment is. And just for simplicity's sake, I reduced it down to just monomorphemes. So in end, I had about 10,000 word types that I was using, and a lot of coffee. So what do we see? So this is a graph very similar to the one we saw for the two words. However, this is over groups of words. And again, x-axis is the segment position where it is in the word. Y-axis is the average segmental information for each segment at the given position. And I've split those 10,000 monomorphemes into two groups, words that are above the median surprisal overall, and words that are below the median surprisal, the blue and the orange. And what do we see? We see that words that are on average more surprising tend to start with more informative material, and words that are less surprising tend to start with less informative material, which is supporting our original sort of hypothesis and guess that we would have words that are more surprising or less predictable based on just frequency to start with more informative material, and the other group would have the other distribution. And a really cool thing that came out of this is, just because we know that word length is also correlated with surprisal, we were able to take the two groups we have there and then just look at the mean word length, and we saw that we got this sort of sanity check that the more predictable words are shorter, the less predictable words are longer, which is sort of a good sign there. And that was just two groups. We split it into quartiles, and we saw the same effect, and even nicer is that they're arranged in the way we'd expect. The most surprising words start with the most surprising material. The least surprising words start with the least surprising material. And finally, this is a really pretty graph, but I mean, doesn't mean anything. So we did a generalized linear model where we were trying to predict segment information. And we try to, and in the model we used the position because we expect later segments to have less information. The word surprisal generally to also affect the model because we see that more surprising words just have more informative material. And an interaction between the two because we see that they all kind of fall off and converge around 5. And what do we see? We see a lot of very, very significant effects, and it's all going in the right way. We see that the position negatively affects it. Surprisal, the more surprising the word, the more informative the material across the word, and we see that the interaction is actually significant, and it does predict this sort of convergence later on in the word. So, wrapping up, Does surprisal words affect the shape? Yes, more surprising words are bigger, less surprising words are smaller. Does the amount of surprisal affect word shape? Yes, more surprising words start with more surprising material or more informative material, and then it kind of trails off. Less surprising words, less surprising material. Is there evidence from online spoken word recognition to support this? Yes, because of incremental processing and sort of the solidification of enhancement and reduction over time. We would expect this. And finally, has this coffee been in vain? I certainly hope not. So now I'd just like to thank everyone for coming here. I'd like to thank the CUNY organizers, Bodo Winter, Mike Hammond, Masha, Noah Nelson, the entire University of Arizona Psycho Lab, and coffee, and the NSF GRFP for paying for the coffee. Thank you. Thank you.
Hi, could you get out your first graph with the 2 lines going down? Your
Yes,
first data
ma'am.
graph. And one really quick clarification question,
Yes.
just because a lot of times I don't understand what's going on.
I don't either.
I'm trying to remind me
Yes.
what surprisal was for you.
Okay, so-
was that word frequency?
It's
Okay,
the inverse
awesome.
word frequency.
It was
Yes.
word frequency,
It was
basically.
inverse word frequency.
Okay, so inverse word frequency, awesome. So if I had an hypothesis walking as like the deflationary hypothesis would simply be that less frequent words have easier, less marked segments. And then I'm trying to think through these measures and to try to figure out to what degree could this just be that less frequent words have more marked segments,
Yes.
right? Well, first off, your measure of segmental information early on, that's going to be carried a lot by the frequency of the segments itself.
Yes.
And probably the frequency, the conditional probability of segment
Right,
2
but
given segment 1.
yeah.
So something like consonant clusters, the ones that are easy, the ones that are
Definitely,
frequent,
yeah.
easy
So
to
that's-
produce. That's going to be eliminated by the end, right? Because all of that prior information is going to wash out the effect of the frequency of the segment, the markedness of the segment, and the markedness of the cluster. So couldn't this just reduce to like that really old idea that as words get more and more frequent, we make them easier and easier to say with less marked segments?
Yes, so this is sort of generally that kind of idea. We would expect that as words get more and more frequent, they would lose the sort of marked things, the things that typologically we don't see. However, we would expect because speakers online will enhance marked segments or just segments in general that are more informative, those weird clusters would stay. So as an example, we have the word no in English, like I know the answer, which historically had a weird KN cluster, and that's a really frequent word, it loses that. Then we have the word sphinx in English, which has this really weird SFA cluster, but you know, there's a lot of other things going on, but that SFA has kept along. So our hypothesis is sort of, because that initial weird cluster or marked cluster is doing more work, it's able to survive longer. Whereas we would expect as these sort of marked segments get start doing less and less work, they're going to get sort of reduced over time, if that answers. And
I'm curious about the relationship between, it seems like the high frequency and low frequency words sort of converge to
Right.
zero surprisal at the same position. So I'm curious, why would it be the case then that you end up getting longer, like more phones in less predictable words, right?
Right,
Because
right.
it seems like because of this like extra information you get in the beginning, they sort of converge at the same place. So like, why did these two things seem to? sort of
Right.
clash
So
like
this
that?
is something I've thought about, and I have some sort of hand-wavy ideas, or sort of more things that would need empirical testing. But the idea would be that you're not surprised, you're not predicting the word. You hit the point at which you should have all the information, but then for the more surprising words, you have all this extra material, and that extra material allows for processing time or something like that, where you can actually take what you've gotten and kind of go and check.
Yeah, I guess you would also want to know something about whether these earlier segments are also hyper-articulated or something. But, yeah.
Okay, it's lunchtime.